In this presentation we will discuss the second law of thermodynamics with its consequences and applications, and introduce the concept of entropy with other thermodynamic potentials. We start with the discussion on the direction of thermodynamic processes in nature and present the second law of thermodynamics in two forms introduced by Kelvin, Planck, and Clausius. Then we treat the problem of reversibility and irreversibility in the context of the second law applied to prove Carnot's theorem and redefine the thermodynamic temperature. Based on Carnot's theorem, we will present an analysis on Clausius inequality as a condition for reversibility or irreversibility of thermodynamic processes. We prove this inequality in the case of Carnot's cycle and a general thermodynamic cycle, and use it to study the thermal efficiency of heat engines. We will also apply Clausius inequality to introduce the fundamental quantity of entropy and reformulate the second law of thermodynamics in terms of entropy production. We determine the entropy of an ideal gas and discuss the production of entropy for various processes in nature. Then we define free energy and free enthalpy that are thermodynamic potentials like energy and enthalpy, and show how thermodynamic processes minimize them at given conditions. In general, we apply the extremum principle for all the potentials in the study of the direction of thermodynamic processes and establish the criteria for thermodynamic equilibrium. We will also derive the fundamental equations of thermodynamics describing the infinitesimal change in thermodynamic potentials. We use the fundamental equation for entropy to determine the conditions for different types of equilibrium in an isolated thermodynamic system. Then we prove Euler's theorem for homogeneous functions and apply it to determine the Euler integrals from the fundamental equations expressing the thermodynamic potentials in terms of the state variables. We will derive the Gibbs-Duham equation from the Euler integrals as well. Finally, we introduce Maxwell's thermodynamic relations between the partial derivatives of the state variables of a system. By presenting an example, we will illustrate how these relations help us to express thermodynamic quantities in terms of those which are not difficult to measure. The first law of thermodynamics states that the energy of the processes taking place in nature is conserved, but it does not tell us whether a process occurs in a given direction or in the opposite one. The first law only imposes a constraint on the energy balance of the thermodynamic processes. If the heat Q is exchanged between a system and its surroundings while a given work W is done on or by the system, we can compare the initial and final states of the system, that is the states before and after the thermodynamic process. Then the first law tells us that the change in the internal energy U of the system is equal to the sum of the heat Q and the work W. However, the first law does not determine the direction of this process. For example, if a ball falling from the given height has a collision with the ground which is not perfectly elastic, then the deformation of the ball produces a given amount of heat warming the ball and its surrounding. The law of conservation of energy states that the heat is equivalent with the energy given by the product of the mass of the ball, the gravitational acceleration and the height. The law of conservation of energy still holds in the reverse process, where the ball at rest on the ground absorbing some heat from its surroundings could ascend at the expense of cooling down the system. The exchange of heat in the collision between the bouncing ball and the ground can be determined, for example, by using a thermal camera detecting the increase of the temperature of the ball. Therefore, we talk about a thermodynamic process which we can reproduce all the time. However, its reverse process never happens. Another simple example is the Joule experiment, where a falling weight drives a paddle while stirring the water in a calorimeter, where the water can be warmed by a rotating paddle while immersed in the liquid. In the inverse process of the Joule experiment, the heat absorbed by the water would be converted to work driving the paddle wheel in the opposite direction and lifting the weight. Although we can perform the Joule experiment whenever we want, we never see that the weight is lifted at the expense of cooling the water. The thing that the reverse direction of these examples and many other thermodynamic processes in nature have in common is some equipment extracts heat from a heat bath, for example from the ground or from a liquid in a calorimeter, and produces a given amount of work equivalent with the heat, for example lift the ball or the weight, while no other change takes place in the system. Since the existence of such a device or engine does not contradict the first law of thermodynamics, it is not a perpetual motion machine or perpetuum mobile of the first kind. However, if such an engine operated on a cycle, it would still be very valuable, since it could convert the virtually inexhaustible amount of heat stored in oceans, the ground or the atmosphere into useful work. Then the engine capable of producing work in such a process was a perpetuum mobile of the second kind, as Wilhelm Ostwald stated in 1893. This fact is summarized in the second law of thermodynamics, stating that a perpetuum mobile of the second kind cannot exist. The original formulation of the second law is dated back to William Thomson, also known as Lord Kelvin, in 1851, which was reformulated by Max Planck in 1897. The Kelvin-Planck statement is the following. It is impossible to construct an engine that extracts heat from a heat reservoir and converts it into work without producing any change. Here the key phrase is without producing any change. A heat engine extracting the heat Q from a hot source and converting it into the useful work W' in a thermodynamic cycle, while the source always has the same temperature T throughout its operation cycle, is forbidden by the second law, if the complete transformation of energy from heat into work is the only final result of the cycle and there is no other effect. For example, a gas during its quasi-static isothermal expansion in a cylinder with a moving piston completely converts the heat extracted from a heat bath into work, but together with other changes. At the end of the process, the piston is located at a different position as a result of the increase in the volume of the gas. In order to restore its original volume, the isothermal expansion must be followed by another step in a thermodynamic cycle, for example the Carnot cycle. However, such a cycle uses another heat bath, a cold reservoir where some amount of the heat is dissipated. In other words, heat engines must exchange heat with two thermal reservoirs, a hot source and a cold sink, as seen in the figure where the heat engine extracts the heat Q1 from the hot source at a high temperature T1, produces the useful work W', and rejects the heat Q2' into the cold sink at a lower temperature T2. Another formulation of the second law of thermodynamics was introduced by Rudolf Clausius in 1850. His statement is equivalent to the Kelvin-Planck statement and also provides a criterion related to the direction of processes in nature. The second law of thermodynamics formulated by Clausius states that heat can never pass from a colder to a warmer body without some change connected therewith, occurring at the same time. In other words, heat never flows spontaneously from a colder body to a hotter body. We can compare this formulation with the Kelvin-Planck statement by rephrasing it the following form. It is impossible to construct an engine that operates in a cycle and produces no effect other than the transfer of heat from a cold reservoir to a hot reservoir. As in the case of the Kelvin-Planck statement, we see restrictions allowing only processes involving some change or other effect besides the heat transfer. It can be illustrated by the examples of refrigerators or heat pumps, where some work is done by the surroundings. In the case of a heat pump operating in a reversed Carnot cycle, the heat is extracted from a thermal reservoir with a lower temperature T2, called cold source, and transferred into another thermal reservoir with a higher temperature T1, called hot sink. On the one hand, external forces do work W' or minus W, and in the other hand, not only the heat minus Q2' is extracted from the colder heat bath and dumped in the warmer one, but some extra heat equivalent to the work done in the process is also absorbed in the hot reservoir. Therefore, the magnitude of the heat minus Q1 delivered to the warmer heat bath is greater than the magnitude of the heat minus Q2' extracted from the colder heat bath. We can also demonstrate the equivalence of the Kelvin-Planck statement and the Clausius statement by showing that if one statement is false, then it necessarily follows that the other statement is also false. In other words, the violation of either statement will result in violation of the other one. First, let us assume that the Clausius statement is false, and there is a heat pump which violates the Clausius statement by removing the heat minus Q2' from the cold reservoir at a temperature T2 to the hot bath at a temperature T1 without any work done on the system. That is, the heat Q1 rejected into the hot bath is equal to the heat Q2' extracted from the cold bath. Such an impossible arrangement is called Clausius violator. Now let us consider a heat engine operating between the same reservoirs at the temperatures T1 and T2. It extracts the heat Q3 from the hot source at the temperature T1, converts a part of this heat into work W', and discards the heat Q2' to the sink at the temperature T1. In this arrangement we used a heat engine that dumps the same amount of heat in the cold reservoir as the one removed from the reservoir by the heat pump. By applying the first law of thermodynamics, the heat Q3 extracted from the hot reservoir can be written as the sum of the heat Q2' dumped in the cold reservoir and the heat delta Q equivalent to the work W' done by the heat engine. In the combined system of the Clausius violator and the heat engine, the net heat removed from the hot reservoir is equal to delta Q, whereas the net heat transfer between the cold reservoir and the combined system is zero. As a result, the combined system can be considered as a heat engine which extracts the net heat delta Q from the hot reservoir and converts it into the useful work W', without rejecting any heat in the cold reservoir. But producing work with a single reservoir contradicts the Kelvin-Planck statement, that is, the combination of the Clausius violator and a heat engine is a Kelvin-Planck violator. In other words, if the Clausius statement is false, the Kelvin-Planck statement must also be false. Conversely, if the Kelvin-Planck statement is false, the Clausius statement must also be false. It can be seen immediately if we combine a heat pump with a Kelvin-Planck violator, where the work produced by the violator is the input work of the heat pump transferring heat from the cold reservoir to the hot reservoir. Then the combined system pumps the heat from the cold bath to the hot bath without any external work, and we obtain a Clausius violator. Therefore, the two forms of the second law of thermodynamics introduced by Kelvin, Planck and Clausius are completely equivalent. When we study the direction of thermodynamic processes, we can divide the processes into two groups, reversible and irreversible processes. We talk about a reversible process if a thermodynamic system evolved from an initial state to another state can be brought back into its initial state without causing any permanent change in its surroundings. Otherwise, the thermodynamic process is irreversible. A simple example for a reversible process is the single swing of a frictionless pendulum, that is a point mass m suspended from a string of the length L, where there is no loss of energy in the frictionless motion. Here the pendulum is initially displaced to one side by a small angle phi, and released from rest. Since its motion is frictionless, the pendulum will retain its initial displacement described by the angle phi after a single swing. We already mentioned the example of a ball bouncing back from a horizontal surface. We can also consider a ball dropped over the stretched rubber sheet from a given height h. If the collision of the ball with the stretched rubber sheet is perfectly elastic and the deformation of the rubber sheet is not permanent, then the bouncing ball can reach its original height h. This result indicates that the perfectly elastic collision is a reversible process. More generally, we can state that any mechanical process without friction or production of heat is a reversible process. In the case of heat production, we talk about thermodynamic processes. In thermodynamics, we also study quasi-static changes in the state of a system, and such processes, for example the Carnot cycle, can be considered reversible ones. We also mention some examples of irreversible thermodynamic processes. The first example of an irreversible process is the production of heat due to friction, that is the conversion of frictional work into heat. When a constant force F is exerted on a body such that it can slide over a surface and covers the distance s, the frictional work depending on the smoothness or roughness of the contact surfaces causes the molecules or atoms on the rubbing surfaces to move faster. That is, these particles gain more kinetic energy and some heat Q is released over the contact surfaces. In Joule's experiment, the work done by the gravitational field pulling the weight and rotating the paddle while immersed in water is also converted to heat in the calorimeter. In order to restore the initial state of the system without any other change, we need a device that was able to extract heat from the previously warmed water in the calorimeter, and transform it into work by lifting the weight without applying any external force. However, such a device would be a perpetuum mobile of the second kind forbidden by the second law. Another example for irreversible processes is the adiabatic expansion of gas in vacuum without any work done on the system by external forces. This process was studied in the Gay-Lussac experiment, and its irreversibility can be shown as follows. In this figure, the gas is initially in the part A of a cylinder sealed by a piston. During the adiabatic expansion of the gas, it moves the piston and fills the part B in the cylinder without exchanging heat with its surroundings. If a spring pushes the piston into its initial position, the gas will be compressed while restoring its initial volume in the part A of the cylinder. But during its compression the gas warms up and the spring does work at the expense of its potential energy. These two effects can only be eliminated by applying such a device that was able to cause for the piston to return to its initial position at the expense of cooling the gas down. Again, such a device would be a perpetuum mobile of the second kind forbidden by the second law. It can be shown that diffusion and thermal conduction are also irreversible processes. Friction and other dissipative processes cannot be eliminated completely, and strictly speaking all the processes in nature are irreversible. Reversible processes are their ideal limiting cases, and therefore invaluable in thought experiments. A consequence of the second law of thermodynamics is Carnot's theorem with two main statements. According to the first one, the thermal efficiency of the reversible Carnot cycle is independent of the material properties of the thermodynamic system performing the cycle. We already saw that the efficiency eta defined by the ratio of the work W' done in the cycle to the heat Q1 absorbed in the cycle is equal to the difference between the heat Q1 and the heat Q2' divided by Q1, where Q2' denotes the heat released in the cycle. This ratio was also expressed as the difference between the temperatures T1 and T2 of the hot and cold heat bath used in the cycle over T1. The first consequence simply tells us that this result holds for an arbitrary working substance performing the cycle. In order to prove the first statement of Carnot's theorem, Let us consider two irreversible Carnot engines C and C bar connected to two heat reservoirs at the temperatures T1 and T2, where the temperature T1 is greater than the temperature T2. We suppose that an ideal gas is applied as working substance in the Carnot engine C, whereas the Carnot engine C bar uses some other working substance. Let us assume that the thermal efficiency eta of the Carnot engine is greater than the thermal efficiency eta bar of the Carnot engine C bar. First, the engine C starts its operation by extracting the heat Q1 from the hot reservoir at the temperature T1, does the work W' given by eta times Q1, and rejects the heat 1 minus eta times Q1 into the cold reservoir at the temperature T2. Then the engine C bar starts its operation in the reverse direction with the amount of working substance allowing the engine to dissipate the heat Q1 into the hot reservoir, compensating the amount of heat extracted by the engine C in the first step. The work W bar done by the engine C bar during its operation is equal to minus eta bar times Q1, and its magnitude is less than the work eta times Q1 done by the engine C as shown in the work balance equation between the two engines. At the same time, the heat 1 minus eta bar times Q1 is extracted from the cold reservoir by the engine C bar, and the heat balance equation states that the extracted heat is greater than the heat 1 minus eta times Q1 rejected into the cold reservoir by the engine C. This relation shows that the whole process cools the cold reservoir. By combining the operations of the two engines, the net work done by them is equal to the difference between eta times Q1 and eta bar times Q1. This expression is positive and the system has done useful work at the expense of cooling the cold reservoir, which is impossible since it violates the second law of thermodynamics. As a result, the assumption that the thermal efficiency eta bar is less than the thermal efficiency eta cannot hold. By reversing the direction of the operation of the whole system, we can prove that the inequality stating that eta bar is greater than eta cannot hold either. Then we conclude that the thermal efficiencies eta and eta bar must be equal, that is, the thermal efficiency of a Carnot engine does not depend on what kind of working substance is used by the engine. The second statement of Carnot's theorem is the following. If a Carnot cycle or any of its infinitesimally small stage is irreversible, then its thermal efficiency is smaller than the ratio of T1 minus T2 to T1, where the hot and cold reservoirs used in the cycle have the temperatures T1 and T2. This consequence can be demonstrated with the concrete example. Let us consider the steps of the isothermal expansion and compression in a Carnot cycle indicated by the curves between the points A and B, and the points C and D on the isotherms at the temperatures T1 and T2 in the pressure-volume diagram of the cycle. We suppose that the Carnot cycle is irreversible because the moving piston of the Carnot engine applying an ideal gas as a working substance has friction with the wall of the cylinder filled with the gas. Since the heat produced by the friction is absorbed at least in part by the heat reservoirs of the engine, the heat Q*1 transferred from the heat bath at the temperature T1 is less than the heat Q1 transferred from the same heat bath in the case of the piston performing a frictionless motion in a reversible process. At the same time, the heat Q'2 rejected to the heat reservoir at the temperature T2 is greater than the heat Q'2 rejected to the same heat reservoir for the piston moving without friction. As a result, the ratio of Q'2 to Q*1 is greater than the ratio of Q'2 to Q1. In the case of the irreversible Carnot cycle, the thermal efficiency eta bar of the cycle is equal to the difference between Q*1 and Q'2 divided by Q*1, or 1 minus the ratio of Q'2 to Q*1. Similarly, the thermal efficiency eta of the reversible Carnot cycle is given by the difference between Q1 and Q'2 divided by Q1, or 1 minus the ratio of Q'2 to Q1. By virtue of the inequality obtained for the ratios in the expressions of the eta bar and eta, the thermal efficiency eta bar of the irreversible process is less than the thermal efficiency eta of the reversible process. Since the expression obtained for eta is equal to 1 minus the ratio of the temperature T2 to the temperature T1, we can write that eta bar is less than 1 minus the ratio of T2 to T1, or the difference between T1 and T2 divided by T1. Then we demonstrated that the thermal efficiency of an irreversible Carnot engine is always less than the difference between T1 and T2 over T1. We saw that the first part of Carnot's theorem states that the thermal efficiency of a reversible Carnot cycle is independent of the material properties of the working substance performing the cycle. The mathematical formulation of the theorem shows that the efficiency depends on only the operating temperatures of the heat reservoirs of the Carnot engine. Based on this fact, we can fix the scale of the thermodynamic temperature already introduced in the discussion on temperature. In order to do that, let us consider the operation of a system that consists of 3 reversible Carnot engines and 3 heat reservoirs at the temperatures T1, T2 and T3. Let us suppose that the first Carnot engine in the system absorbs the heat Q1 from the heat bath at the temperature T1, does the work W1' and rejects the heat Q2' to the heat bath at the temperature T2. Similarly, the second Carnot engine extracts the heat Q2 from the heat bath at the temperature T2, delivers the work W2' and dissipates the heat Q3' to the heat bath at the temperature T3. Here we assume that the same amount of heat is rejected to and absorbed from the heat reservoir at the temperature T2, that is, the heat Q2 is equal to the heat Q2'. Finally, we also suppose that the third Carnot engine absorbs the heat Q1, that is the same heat from the heat reservoir at temperature T1 as the first reversible heat engine does the work W3', and rejects the heat Q3', that is the same amount of heat to the heat reservoir at the temperature T3 as the third reversible heat engine does. Now we determine the thermal efficiency for each reversible engine during its operation. The thermal efficiency eta1 of the first Carnot engine is defined by the ratio of the work W1' done by the engine to the heat Q1 absorbed in the Carnot cycle. We already saw that the work W2' can be written as the difference between the heat Q1 absorbed by the engine and the heat Q2' rejected by it due to the first law of thermodynamics. Then the efficiency is simply equal to 1 minus the ratio of Q2' to Q1. Similarly, the thermal efficiency eta2 of the second reversible engine defined by the ratio of the work W2' delivered by the engine to the heat Q2 absorbed by it, is equal to 1 minus the ratio of the heat Q3' rejected by it to the heat Q2. Since we assume that Q2 is equal to Q2', we can write the efficiency as 1 over Q3' divided by Q2'. Finally, the thermal efficiency eta3 of the third Carnot engine defined by the ratio of the work W3' done by the engine to the heat Q1 absorbed by it, is equal to 1 minus the ratio of the heat Q3' rejected by the engine to the heat Q1. Since the thermal efficiency of a reversible Carnot engine does not depend on the material properties of its working substance, as stated in Carnot's theorem, the efficiency has the same value for given temperatures of the heat reservoirs used by the engine. As a result, the ratio of the magnitudes of the heat absorbed and rejected in the Carnot cycle depends only on these temperatures. We already derived the explicit dependence of the efficiency on the temperature for a Carnot engine using an ideal gas as a working substance, and Carnot's theorem states that this explicit form is valid for any other type of working substance. However, we keep the dependence of the efficiency on the temperature in a general form, and we only conclude that the ratio of Q2' to Q1 is some function f of the temperatures T1 and T2 of the heat reservoirs exchanging heat with the first engine. Similarly, the ratio of Q3' to Q2' can be written as the function f depending on the temperatures T2 and T3, and the ratio of Q3' to Q1' can be written as the function f depending on the temperatures T1 and T3. Now we can multiply and divide the ratio of Q3' to Q1 by Q2', and write it as Q3' over Q2' times Q2' over Q1. If we substitute the functional dependencies of these fractions on the temperature into this equation, we can state that the function f depending on T1 and T3 is equal to the function f depending on T2 and T3, times the function f depending on T1 and T2. The left-hand side of the equation does not depend on the temperature T2, whereas its right-hand side does. Then we conclude that the function f depending on T1 and T2 has the form given by the ratio of another function g depending on T1 to the function g depending on T2. Similarly, the function f depending on T2 and T3 can be written as the ratio of the function g depending on T2 to the function g depending on T3. If we substitute these forms into the right-hand side of the last equation, we can write the function f depending on T1 and T3 as the ratio of the function g depending on T1 to the function g depending on T3. Generally, we can write that the ratio of the heat Q' rejected to any of the heat reservoir in the system to the heat Qj absorbed from another one is equal to the ratio of the function g depending on the temperature Ti to the function g depending on the temperature Tj, where the indices I and j can be 1, 2 and 3. Here the function g is some monotonic function of temperature satisfying these relations, but it is not determined yet. When Lord Kelvin defined the scale of thermodynamic temperature, he simply selected the identity function for g, and established the relation stating that the ratio of the absorbed heat to the rejected heat is equal to the ratio of the temperature of the cold reservoir to the temperature of the hot reservoir. As a result, the thermal efficiency eta1 of the first reversible heat engine is equal to 1 minus the ratio of the temperature T2 to the temperature T1. We have similar expressions for the thermal efficiencies of the other two engines as well. We already mentioned that this equation is derived for a Carnot engine using an ideal gas as a working substance, and later it was generalized in Carnot's theorem. Therefore, The choice made by Kelvin gives the correct form for the temperature dependency of the efficiency. This equation can be used to express the temperature T2 of one of the heat bath as the temperature T1 of the other one, times 1 minus the thermal efficiency eta of the reversible Carnot cycle. We can establish the thermodynamic temperature by fixing the temperature T1 as a reference temperature, and measure the thermal efficiency eta of the Carnot cycle. In practice, we choose the triple point of water as the reference temperature T1, which is equal to 273.16 Kelvin. Since the heat absorbed in the Carnot cycle is equal to the work done in the first step of the cycle, that is the isothermal expansion of the gas, the thermal efficiency is just equal to the total work done in the cycle divided by the work done in the first step. By measuring it in the reversible Carnot cycle, we can determine the thermodynamic temperature T2 for the reference temperature T1 of the triple point of the water. We note that because the reversible Carnot cycle is just an idealized approximation, we cannot obtain accurate values for the thermodynamic temperature by applying this method. However, the Clausius-Clapeyron equations can be derived from the equation defining the thermodynamic scale of temperature, and the comparison of their graphs with measurements can provide accurate values for the thermodynamic temperature. We can cast the second law of thermodynamics into a pure mathematical form that is called Clausius' theorem or Clausius inequality. First, we derive Clausius inequality for a heat engine exchanging heat with two thermal reservoirs, a hot source and a cold sink in a Carnot cycle represented with the closed curve A, B, C and D in the pressure-volume diagram. As the figure of the heat engine and the thermal reservoirs operating in the Carnot cycle shows, the engine absorbs the heat Q1 from the hot source at the temperature T1 in the step of isothermal expansion of the working substance along the curve between the points A and B in the pressure-volume diagram. By completing the cycle, the heat engine delivers the work W' given by the area of the closed shape A, B, C and D, while it rejects the heat Q2' to the cold sink at the temperature T2 in the step of isothermal compression along the curve between the points C and D. We saw that the thermal efficiency eta of a Carnot cycle defined by the ratio of the work W' done by the heat engine to the heat Q1 absorbed by the engine is equal to the ratio of the difference between the heat Q1 and the heat Q2' to the heat Q1 due to the law of conservation of the energy. Carnot's theorem states that this value obtained for the thermal efficiency eta is always less than or equal to the difference between the temperatures T1 and T2 of the hot source and the cold sink divided by the temperature T1. If the Carnot cycle is reversible, then the equality holds, whereas the efficiency is less than this ratio for an irreversible cycle, which can also be written as 1 minus the ratio of the temperature T2 to the temperature T1. Since the heat Q2' rejected to the cold reservoir is equal to minus the heat Q2 absorbed from it, the thermal efficiency eta can also be expressed as the ratio of the sum of the heat Q1 and the heat Q2 to the heat Q1, where both Q1 and Q2 denote the heat delivered to the engine from the thermal reservoirs. Obviously, a positive value of the heat Q2' rejected by the engine results in a negative value of the heat Q2 delivered to the engine. Then the left-hand side of the equation is given by 1 plus the ratio of Q2 to Q1, and this value is less than or equal to 1 minus over T2 to T1. As a result, we can write that the ratio of Q2 to Q1 is less than or equal to minus the ratio of T2 to T1. If we multiply this expression by Q1 and divide it by T2, we obtain another form of the expression stating that the ratio of the heat Q2 to the temperature T2 is less than or equal to minus the ratio of the heat Q1 to the temperature T1. In this expression, each ratio of the heat to the temperature characterizes the transport of energy in one step of the Carnot cycle, where the heat is exchanged between one of the thermal reservoirs and the heat engine in an isothermal process at the temperature of the thermal reservoir. Motivated by this fact, Clausius introduced the concept of reduced heat and defined it by the ratio of the heat absorbed from a heat bath in an isothermal process to the temperature of the heat bath. Then the ratios Q1 over T1 and Q2 over T2 are the reduced heat exchanged by the heat engine and the thermal reservoirs in the Carnot cycle, and Clausius inequality can be formulated as follows. The sum of the reduced heat in each isothermal step of the Carnot cycle cannot be greater than 0. That is the ratio of the heat Q1 absorbed from the thermal bath to the temperature T1 of the thermal bath, plus the ratio of the heat Q2 absorbed from the thermal bath to its temperature T2 of the thermal bath is less than or equal to 0. The sum of the reduced heat only vanishes if the Carnot cycle is reversible, otherwise this sum is less than 0. This result can be generalized to any cyclic process in thermodynamics in the following way. Let us consider a thermodynamic cycle represented by the closed curve calligraphic C in the pressure-volume diagram, where the arrow on the curve indicates the direction of the cycle. We also draw a Carnot cycle such that its states A and C are on the curve calligraphic C representing the thermodynamic cycle, where the heat is absorbed from two heat reservoirs at the temperatures Ti and Tj. As already seen, the steps of isothermal expansion and compression in the Carnot cycle are represented by the curves between the points A and B, and the points C and D along the isotherms, that is the red hyperbolas. The adiabatic processes in the cycle take place between the states B and C, and the states D and A along the adiabats represented by the yellow curves. Let delta Q star I and delta Q star J denote the heat absorbed from the thermal reservoirs at the temperatures Ti and Tj during the isothermal expansion and compression of the cycle. Now we consider another Carnot cycle represented by the closed curve connecting the points A', B', C' and D' with the isotherms at the temperatures Tk and Tl, where the states A' and D' are on the adiabat connecting the states B and C of the first Carnot cycle. Here the heat absorbed from the heat reservoirs at the temperatures Tk and Tl are denoted by delta Q star K and delta Q star L. We already derived Clausius inequality for Carnot cycles, and we can write that the ratio of the heat delta Q star I to the temperature Ti, plus the ratio of the heat delta Q star J to the temperature Tj must be less than or equal to 0 for the Carnot cycle between the states A, B, C and D. We have the same inequality for the second Carnot cycle as well, only the indices I and J must be replaced with the indices K and L. If we consider the combination of the Carnot cycle A, B, C and D, and the Carnot cycle A', B', C' and D', then we need to add the ratio of delta Q star K to Tk and the ratio of delta Q star L to TL to the left-hand side of the Clausius inequality. Since the two Carnot cycles have opposite orientations along the adiabat between the states B and D', their contributions cancel out each other along the curve between the points B and D' in the total work given by the integral along the closed curves of the cycles. As a result, we can replace the two Carnot cycles with one thermodynamic cycle connecting the states A and B, B and A' and B', B' and C', C' and D', D' and C, C and D, and finally D and A. This result indicates that an arbitrary thermodynamic cycle can be constructed from, or at least approximated with a series of Carnot cycle when we study the exchange of heat in that process. In order to proceed with such a construction or approximation, we have to examine the exchange of heat in both the thermodynamic cycle and its approximation with Carnot cycles. The pressure-volume diagram shows that the states A' and A are connected with two different paths. The path along the curve calligraphic C, and the paths connecting the states A and B, and the states B and A'. Here we reverse the orientation of the path between the states A and A' along the curve so that it could form a cycle with the paths connecting the states A, B, and A'. Since the thermodynamic process between the states B and A' is adiabatic, delta Q star I gives the total amount of heat exchanged in the process with the steps AB and BA'. However, the amount of heat is generally not equal to the magnitude of the heat delta Qi absorbed in the process represented by the curve C between the states A' and A. Similarly, the magnitude of the heat delta QL absorbed in the process along the curve calligraphic C between the states C and C' is generally different from the magnitude of the heat delta Q star L absorbed in the steps CD' and D'C'. Again, the path connecting the states C and D' is an adiabat where there is no exchange of heat. Now we can consider the closed path connecting the states A', and B as a mini-thermodynamic cycle. Similarly, the closed curve connecting the points C', C, and D' also represents a thermodynamic cycle. Then we can apply the first law of thermodynamics for these cycles, stating that the net heat absorbed in the mini-cycles must be equal to the work done in the cycles. The net heat absorbed in the first cycle is given by the difference between delta Q star I and delta Qi, which is equal to the work W' given by the green area of the plane figure defined by the points A', A, and B. The negative sign of the heat delta Qi indicates that the mini-cycle between the states A and A' and the thermodynamic cycle represented by the curve calligraphic C have opposite orientations. The same equation can also be written for the cycle C', C, D' with the index L instead of the index I and with the work W' given by the green area of the plane figure C, C', D'. Although this area is small, the plane figure A', B has a considerable size. Then the work W done in the first mini-cycle, that is the difference between the heat delta Q star I and the heat delta Qi, is not negligible. However, we can approximate the thermodynamic cycle represented by the curve calligraphic C with the series of Carnot cycles constructed from a dense network of isotherms and adiabats, where the total area of the cycles almost covers the area of the closed curve calligraphic C in the pressure-volume diagram. For the sake of brevity, we show only the sections of isotherms and adiabats forming the Carnot cycles. We also denote the intermediate states by capital letters only for two adjacent Carnot cycles. In the series of Carnot cycles, all the adjacent cycles share a path connecting two states, for example the states B and D', but they evolve along it in the opposite direction with respect to each other. As a result, the effects along the path cancel out for each adjacent pair of the Carnot cycles, and the closed curve calligraphic C can be replaced by the paths connected by the points A, B, A', B', ellipsis, C', D', C, D and so on. We can therefore approximate the thermodynamic cycle represented by the curve C with this series of Carnot cycles, where the n isotherms are used for their constructions, that is, the heat is absorbed from n different thermal reservoirs. Here delta Q star 1, delta Q star 2, ellipsis, delta Q star n denote the heat absorbed from the heat reservoirs at the temperatures T1, T2, ellipsis Tn, and the Clausius inequality for the series of Carnot cycles in this construction tells us that the sum of the ratio of the absorbed heat delta Q star I to the temperature Ti from I equal to 1 to n is less than or equal to 0. In other words, the net reduced heat absorbed from all thermal reservoir in the sequence of the cycles is never positive. We see that the area of the plane figure A, B in the pressure volume diagram representing the work W' done in the mini-cycle A, B is small. Due to the first law, the difference between the heat delta Qi absorbed in the process evolving from the state A to the state A' along the curve calligraphic C and the heat delta Q star I absorbed in the process with the steps AB and AB' is also small. For each mini-cycle along the curve calligraphic C, we can compare these differences between the heat absorbed in a given section of the thermodynamic cycle and the heat absorbed in the processes along the paths constructed from the Carnot cycles. Then we find that these differences will be small provided the areas between the curve calligraphic C and these paths are also small. If we apply a more and more dense network of isotherms and adiabats, that is, increase the number of Carnot cycles in the construction with the number of the thermal reservoirs such that n tends to infinity, the work W' given by these areas also tends to 0. As a result, the difference between delta Qi and delta Q star I goes to 0 for each adjacent pair of Carnot cycle where the index I runs from 1 to n. In other words, as the number n of the thermal reservoirs used in the construction approaches infinity, the processes approximating the thermodynamic cycle also approach the cycle and the heat delta Q star I tends to delta Qi. Then we conclude the following theorem. If a system absorbs the amounts of heat delta Q1, delta Q2, ellipsis, delta Qn from the thermal reservoirs at the temperatures T1, T2, ellipsis, Tn in a thermodynamic cycle, then the Clausius inequality holds, stating that the sum of delta Qi divided by Ti from I equals to 0 to n is less than or equal to 0 in the limiting case where n tends to infinity. Since the absorbed heat delta Qi approaches 0 as the number n of the thermal reservoirs goes to infinity, the infinite sum becomes a cyclic integral of 1 over the temperature T with respect to the heat Q, and the Clausius inequality states that the cyclic integral of the reduced heat absorbed in the thermodynamic system is never greater than 0. If the thermodynamic cycle is reversible, then the infinite sum or the cyclic integral vanishes, otherwise it is less than 0. There is a corollary of the Clausius inequality which is related to the thermal efficiency of any thermodynamic cycle or heat engine. Let us consider a thermodynamic cycle with n steps, that is, where the working substance exchanges heat with 2 times n thermal reservoirs. Here we can see the pressure-volume diagram of the cycle as shown in the proof of the Clausius inequality. We assume that the number n of the steps is very large, and the thermodynamic cycle is represented by the purple path along the isotherms and the adiabats. Then the curve calligraphic C represents the limit of the thermodynamic cycle in the diagram as the number n tends to infinity. Let delta Qi with the superscript 1 denote the heat absorbed from a hot source at the temperature Ti, and let delta Q'J with the superscript 2 denote the heat rejected to a cold sink at the temperature Tj. By definition, both delta Q super 1 sub I and delta Q prime super 2 sub j are positive quantities, and their sums give the total heat Q1 absorbed from all the hot sources and the total heat Q prime 2 discarded to all the cold sinks respectively. Then the Clausius inequality can be written as the sum of delta Q super 1 sub I divided by Ti from I equal to 1 to n, minus the sum of delta Q prime super 2 sub j divided by Tj from j equal to 1 to n is equal to or less than 0. Here the negative sign of the second sum in the left-hand side of the inequality indicates that the heat appearing in the numerator of the fraction is rejected to the cold sinks. Now we assume that the thermal reservoir at the temperature T1 is the hottest source used in the thermodynamic cycle, where the isotherm at the temperature T1 gives the path of a step with an isothermal expansion of the cycle between the states A double prime and B double prime. Similarly, we assume that T2 is the temperature of the coldest sink used in the thermodynamic cycle, where the isotherm at the temperature T2 gives the path of a step with an isothermal compression of the cycle between the states C double prime and D double prime. Since the temperature T1 is greater than the temperature Ti of any other hot source used in the cycle, by replacing Ti with T1 in the first sum in the left-hand side of the Clausius inequality, we obtain a sum which cannot be greater than the original one. Similarly, since the temperature T2 is less than the temperature of any other cold sink used in the cycle, the sum obtained after the replacement of Tj with T2 in the left-hand side of the inequality cannot be less than the original expression of the second sum. As a result, the modified form of the first sum, minus the modified form of the second sum cannot be greater than the original form of the first sum, minus the original form of the second sum, which is the left-hand side of the Clausius inequality. Then we obtain the following inequality. The ratio of the sum of delta Q super 1 sub I to T1, minus the ratio of the sum of delta Q super 2 sub J to T2 is less than or equal to 0. Here the sum in the numerator of the first fraction is equal to the total heat Q1 absorbed in the thermodynamic cycle, whereas the sum in the numerator of the second fraction gives the total heat Q'2 rejected in the cycle. Now we write the inequality stating that the heat Q1 times the ratio of the temperature T2 to the temperature T1 is less than or equal to the heat Q'2. The thermal efficiency eta of an arbitrary thermodynamic cycle or a heat engine is defined by the ratio of the work W' done in the cycle to the total amount of heat Q1 absorbed in the cycle. Here the work W' is given by the total area of the steps forming the whole cycle, and the first law of thermodynamics states that it is equal to the difference between the heat Q1 absorbed in the cycle and the heat Q'2 rejected in the cycle. By substituting the inequality obtained here into Q'2, we see that this fraction is less than or equal to 1 minus the ratio of T2 to T1, or the ratio of the difference between the temperature T1 of the hottest source and the temperature T2 of the coldest sink to the temperature T1. Then we have proven that the maximum of the thermal efficiency of a thermodynamic cycle or a heat engine equal to this ratio is a corollary of the Clausius inequality. Since eta is less than 1, we conclude that the heat cannot be completely converted into work by a heat engine, or more generally in a thermodynamic cycle. Since the Clausius inequality is a mathematical formulation of the second law of thermodynamics, it can also be used to introduce a new thermodynamic function called entropy and reformulate the mathematical expression of the second law. Let us assume that a thermodynamic system depicted in the pressure-volume diagram evolves from the state A to the state B along a path represented by the curve C1, and then it is brought back to its initial state A along another path represented by the curve C2 in a reversible thermodynamic cycle. Then the Clausius inequality states that the cyclic integral of 1 over the temperature T of the system with respect to the heat Q rev absorbed in the reversible process vanishes. We can break up the cyclic integral into a sum of a line integral along the path C1 from the state A to the state B, and a line integral along the path C2 from the state B to the state A. Since we can reverse the orientation of the second line integral along the curve C2, the integral of the reduced heat along the path C1 from the state A to the state B is equal to the integral of the reduced heat along the path C2 from the state A to the state B. In other words, the integral of the reduced heat depends only on the initial state A and the final state B, and is independent of the path along which the reversible process takes place between the states A and B. Since the initial state A and the final state B of the process are completely determined by the state variables of the thermodynamic system describing those states, the line integral of the reduced heat of the system is also a unique function of the state variables describing the states A and B. Motivated by this fact, Clausius introduced a new state function, that is a thermodynamic function depending only on the state of a system like its internal energy or its enthalpy. This state function is called the entropy S of a thermodynamic system and it is defined as follows. The difference between the entropy S of the system and the states B and A is given by the line integral of 1 over the temperature T of the system with respect to the heat Q rev absorbed by the system along an arbitrary path in a reversible process between the states A and B. This definition shows that the unit of entropy is the ratio of the unit of heat to the unit of absolute temperature. In SI, the unit of entropy is joule per Kelvin. The only issue with this definition is that thermodynamic processes in nature are always irreversible in a strict sense, and they cannot be applied in the determination of the entropy difference in the definition. However, if we consider the idealized limiting case of quasi-static reversible processes bringing the system from the state A to the state B, that can be used to determine the difference between the entropy of a thermodynamic system in two different states. Like internal energy, entropy is defined up to an arbitrary additive constant. The value of entropy can therefore be chosen as 0 in an arbitrary state P0, and the entropy S of a thermodynamic system in the state P is defined by the line integral of 1 over the temperature T of the system with respect to the heat Q rev absorbed in a reversible process, from the null state P0 to the state P along any path represented by the curve C in the state space of the system. As in the case of the definition of the change in entropy, this definition shows that the unit of entropy is given by the ratio of the unit of heat to the unit of absolute temperature and its SI unit is joule per Kelvin. An equivalent definition of entropy can also be given in the following form. If a thermodynamic system absorbs the infinitesimal amount of heat Q rev at the temperature T in a reversible process, then the infinitesimal change in the entropy S of the system is equal to the ratio of the absorbed heat dQ rev to the temperature T. We saw that entropy is a state function, that is the line integral of the reduced heat in the right-hand side of the previous definition of entropy depends only on the initial and final points of the path of integration but it is independent of the path. As a result, the left-hand side of this definition is an exact differential, namely the exact differential of the entropy S. Then we can rephrase the first two theorems of thermodynamics in differential form. The first law states that the infinitesimal change in the internal energy U of a system is equal to the infinitesimal amount of heat Q exchanged between the system and its surroundings, plus the infinitesimal work W done in the process of heat exchange. The second law states that the infinitesimal change in the entropy S of the system given by the ratio of the infinitesimal amount of heat Q rev absorbed by the system in a reversible process to the temperature T of the system, is an exact differential. The definition of entropy given by the integral of the reduced heat of a thermodynamic system in a reversible process is formally equivalent to the definition of the potential energy of a mass point moving in a conservative force field. We saw that the entropy S of a thermodynamic system in the state P is defined by the line integral of 1 over the temperature T of the system with respect to the heat Q rev absorbed by the system along any reversible path calligraphic P from a null state P0 to the state P in the state space of the system. In dynamics, the potential energy E pot of a point mass moving under the influence of a conservative force F at an instantaneous position P is defined by minus the line integral of the force field F with respect to the arc length S along an arbitrary path calligraphic P from the point P0 representing a null point to the point P. Based on the definition applying the integral of reduced heat, we define the differential of entropy S by the ratio of an infinitesimal amount of heat Q rev absorbed during an infinitesimal reversible change in the state of the system, to the temperature T of the system. As a result, we saw that the infinitesimal change of the entropy is an exact differential. Similarly, this definition is equivalent to the statement that the differential of the potential energy E pot of a point mass is given by minus the scalar product of the conservative force F acting on the point mass and the infinitesimal displacement ds of the point mass. The infinitesimal change in the potential energy is therefore an exact differential. If a reversible process is adiabatic, that is, no heat is exchanged between the thermodynamic system and its surroundings, then the differential of Q rev vanishes. By applying the integral definition of the entropy S, we can conclude that the difference of entropy between the states P and P0 also vanishes. If P0 is a null state, then the entropy is identically zero. The differential of the entropy S vanishes as well, and both the equations show that the change in entropy is zero. In other words, the entropy S of a system is constant during a reversible adiabatic process. We call any process with constant entropy isentropic process, and we can conclude that reversible adiabatic processes are isentropic processes. In the case of a conservative force F acting on a point mass, we can talk about the motion over equipotential surfaces defined by the vanishing scalar product of the force F and the infinitesimal displacement ds of the point mass. That is, any displacement perpendicular to the force F is over an equipotential surface, where the difference in the potential energy E pot of the point mass between the point P and the point P0 vanishes. Since P0 is a null point, the potential energy is zero for the motion along the equipotential surface. Then the differential of the potential energy vanishes as well, that is, E pot is constant during the motion, as the name of the equipotential surface indicates. As a result, we can state that the potential energy of a point mass is constant while it moves over an equipotential surface of a conservative force field. All these statements show an analogy between reversible processes and conservative forces. We applied the Clausius inequality to introduce the concept of entropy, and we can also use it to study the principle of entropy production. Let us consider a thermodynamic system evolving from the initial state A to the state B in an irreversible process along a path represented by the curve C or in the pressure volume diagram. Then it is brought back to the state A along a different path represented by the curve C Rev in a reversible process. As a result, we can talk about an irreversible thermodynamic cycle where the Clausius inequality holds, that is, the cyclic integral of the reduced heat of the system is strictly less than zero. Now we decompose the cyclic integral into the sum of integrations performed along the irreversible and reversible paths. Here the direction of the process along the individual paths is indicated by the superscripts of the curve CR and CR. Then we state that the integral of the reduced heat of the system between the states A and B in the irreversible process, plus the integral of the reduced heat between the states B and A in the reversible process is less than zero. If we apply the definition of entropy, then we see that the second integral along the reversible path in the left-hand side of the inequality is simply equal to the difference in the entropy S between the states A and B. By reordering the terms, we can write that the difference in the entropy S of the system between its states B and A is greater than the integral of the reduced heat of the system along an irreversible path between the states A and B. In other words, the increase in entropy, that is the production of entropy, is always greater than the sum or the integral of the reduced heat of the system in an irreversible process. Let us suppose that the thermodynamic system is isolated and there is no exchange of energy between the system and its surroundings. A non-isolated system can be made isolated by supplementing the system with the bodies interacting with it. Since no heat is exchanged in the case of an isolated system, even the infinitesimal change Q in the heat is zero. As a result, the integral of the reduced heat of the closed system vanishes, and we can write that the difference in the entropy S of the system between the states B and A is greater than zero. Then we conclude that the entropy of an isolated system increases during an irreversible process in the system. In the idealistic limiting case of reversible processes, the entropy of an isolated system is constant. Therefore, the change delta S in entropy is never negative in an isolated system. This is the principle of entropy production, which is one of the most important form of the second law of thermodynamics. This principle tells us that thermodynamic processes can only take place in an isolated system until the entropy of the system reaches its maximum, as it can be seen from the following arguments. If the entropy of an isolated system has maximum, then we have two possibilities. Either the state of the system does not change anymore and the system is in thermodynamic equilibrium, or any further transformation of the state of the system is a reversible process with constant entropy. However, reversible processes represent the limit of an infinite number of successive equilibrium states during the transformation of the state of a system, which is just an idealized case and does not occur in nature. As a result, the principle of entropy production involves that an isolated system has maximum entropy in thermodynamic equilibrium. Let us suppose that an isolated system evolves from the initial state A to the final state B along the path P in the n-dimensional state space of the system. If the entropy of the system reaches its maximum at the state B, then the entropy increases along the path P. Since entropy is a state function, it is a unique function of the state vector x of the system combined from the state variables x1, x2, ellipsis, xn of the system. An infinitesimal change in the entropy S is greater than or equal to zero, and its differential can be expressed in the terms of its partial derivatives with respect to the state variables xi. As a result, the sum of the product of the partial derivatives of entropy and the differentials of the state variables must be non-negative, but the principle does not generally provide conditions for the partial derivatives themselves. We consider Joule's free expansion experiment as an example. It is an irreversible adiabatic process in which an ideal gas expands into an insulated evacuated chamber, and it could be approximated as an isothermal process due to the negligible difference in the gas temperature measured before and after its expansion. Then the isothermal expansion of the gas in its state space, that is in its pressure-volume temperature diagram, is represented by the path calligraphic P between the initial state A and the final state B along one of the isotherm. For any infinitesimal displacement along the path calligraphic P, the differential of the temperature T vanishes, the differential of the volume V is positive and the differential of the pressure P is negative. Then we have only a criterion stating that the partial derivative of the entropy S of the gas with respect to its volume V times dV must be greater than or equal to the partial derivative of the entropy S with respect to the pressure P times dP. This indeterminacy also indicates that in order to determine the entropy production while the state of a given amount of ideal gas changes, two of the three state variables of the gas have to be fixed. Now the first two laws of thermodynamics can be formulated as follows. The first law states that the energy of an isolated system is constant, whereas the second law states that the entropy of an isolated system can only increase or remain constant. The principle of entropy production determines the direction of processes in nature by forbidding such processes in an isolated system, which would reduce the entropy of the system. The free expansion of an ideal gas demonstrate this fundamental anti-symmetry in the direction of processes. The reverse direction of such a process is impossible in nature, that is, a spontaneous reduction of the volume of an ideal gas in a vessel is forbidden by the principle, because the entropy production was negative in the process. Some scientists, like Benjamin Thomas, Helmholtz and Canon Georges Lemaitre, draw a cosmological implication of the principle and formulated the theory of heat death, stating that the Earth or even the universe would unfit for habitation of human within a finite period of time. Helmholtz assumed that the universe in a continuous thermodynamic process will eventually reach the state of maximum entropy, where all the available energy will have been expended and no more activity will occur in the state of eternal rest or heat death. After the introduction of the Big Bang theory with a continuous expansion of the universe from a primordial singularity, Lemaitre rephrased this assumption by stating that the expanding universe slows down, becomes more diffused, and it will eventually reach the state of maximum entropy, which is a final equilibrium state of heat death. From the standpoint of modern physics, this conclusion is incorrect. First of all, the principle of increase in entropy holds true only for closed and finite systems. Furthermore, the second law has a probabilistic nature describing the probable course of events, from which deviations are possible even if only with a small probability. We illustrate entropy production with some examples. In the first example, we will determine the entropy and its change of an ideal gas. If a given amount of ideal gas absorbs the infinitesimal amount of heat Q rev at the temperature T in a reversible change of state, then we can apply the first law of thermodynamics telling us that the differential of the internal energy U of the gas is equal to the infinitesimal amount of heat Q rev minus the infinitesimal amount of work W prime done by the expanding gas. Here the work dW prime is simply equal to the pressure volume work given by the pressure P of the gas times the infinitesimal change in its volume V. Then we can express the absorbed heat dQ rev as the differential of the internal energy U of the gas, plus its pressure P times the differential of its volume V. For the reversible expansion of the gas, the second law of thermodynamics tells us that the differential of the entropy S of the gas is equal to the ratio of the infinitesimal amount of heat dQ rev to the temperature T of the gas. By substituting the expression obtained for dQ rev into the second law, the infinitesimal change in the entropy S of the gas can be written as the ratio of du plus P times dV, to T. For an ideal gas of mass m, the infinitesimal change in its internal energy is given by the mass m times the specific heat capacity Cv of the gas for constant volume, times the infinitesimal change in its temperature T. We can also apply the ideal gas law stating that the pressure P times the volume V is equal to the mass m times the specific gas constant Rs of the gas times the temperature T, to express the pressure P of the gas as its mass m times its specific gas constant Rs times its temperature T divided by its volume V. Then the infinitesimal change in the entropy S of the ideal gas is equal to its mass m times the sum of the specific heat capacity Cv times the ratio of the infinitesimal change in the temperature T to the temperature T, and the specific gas constant Rs times the ratio of the infinitesimal change in the volume V to the volume V. Let us suppose that the initial state A and the final state B of the expanding ideal gas are described by the pair volume V1 and temperature T1 and the pair volume V2 and temperature T2 in the temperature versus volume graph. We can compute the difference in the entropy S of the ideal gas between the states B and A by integrating the differential of S along any reversible process between the initial and final states. Since the process is reversible, we can choose any path for the integration to our convenience. When studying entropy production, we saw that it is always useful to study the transformation of the state of an ideal gas along a path in the state space where only one state variable changes. Then we can decompose any reversible process between the two states A and B into the following quasi-static processes. The first process is an isochoric warming of the gas, where we bring the gas from the state A into another state C at the temperature T2 while its volume is held constant and the differential of the volume V of the gas vanishes. The state variables in this intermediate state C are given by the pair V1 and T2. The second process, an isothermal expansion, where the gas is brought from the intermediate state C into the state B while its temperature T2 is held constant and the differential of the temperature T of the gas is 0. As a result, we can break the integral into two terms, an integral with respect to the entropy along the path between the states A and C, and another integral with respect to the entropy along the path between the states C and B. Since the first process is an isochoric one, we need to integrate the expression obtained for the differential of the entropy S with respect to the temperature T from the temperature T1 to the temperature T2. Evidently, the second term in the parentheses in the expression obtained for the differential of the entropy does not depend on the temperature and it has no contribution to the integral. Similarly, since the second process is an isothermal one, the differential of the entropy S must be integrated with respect to the volume V from the volume V1 to the volume V2, where the first term in the parentheses in the expression obtained for the differential of the entropy has no contribution to the integral. By performing the integration, we conclude that the change in the entropy S of an ideal gas in a reversible transformation of its state from the state A to the state B, is given by its mass m, times the sum of the specific heat capacity CV of the gas for constant volume, times the natural logarithm of the ratio of its final temperature T2 to its initial temperature T1, and its specific gas constant Rs times the natural logarithm of the ratio of its final volume V2 to its initial volume V1. We can cast this equation in another form if we introduce the specific entropy and volume of the ideal gas. The specific entropy of the gas is defined by the ratio of its entropy S to its mass m, and its SI unit is joule per kilogram Kelvin. Similarly, the specific volume of the gas is given by its volume V over its mass m, and its SI unit is cubic meter per kilogram. The specific properties of a thermodynamic system are usually denoted by small letters. By applying these definitions, we can write the change in the specific entropy S of an ideal gas as its specific heat CV times the natural logarithm of the ratio of its final temperature T2 to its initial temperature T1, plus the specific gas constant Rs of the gas times the natural logarithm of the ratio of its final specific volume V2 to its initial specific volume V1. In this formula, the change in entropy is expressed in terms of the pair of temperature and volume, and it can also be expressed in terms of the pair of volume and pressure or in terms of the pair of temperature and pressure from the ideal gas law. If the ideal gas law is formulated in terms of the specific volume of the gas, then it states that the pressure P of the gas times its specific volume V is equal to its specific gas constant Rs times its absolute temperature T. Now we express the gas temperature T from the law as the pressure P times the specific volume V over the specific gas constant Rs, and the specific volume V of the gas as the specific gas constant Rs times the temperature T over the pressure P, and substitute these expressions in the fractions in the equation of entropy production. Then the natural logarithm of the ratio of T2 to T1 is equal to the natural logarithm of the ratio of P2 times V2 to P1 times to V1, which can be written as the logarithm of the ratio of P2 to P1, plus the logarithm of the ratio of V2 to V1. Similarly, the natural logarithm of the ratio of V2 to V1 is equal to the natural logarithm of the ratio of T2 times P1 to T1 times to P2, which can be written as the logarithm of the ratio of T2 to T1, minus the logarithm of the ratio of P2 to P1. If we substitute the expression obtained for the logarithm of the ratio of the final and initial temperatures in the right-hand side of the equation of entropy production, then we can state that delta S is equal to CV times the logarithm of the ratio of P2 to P1, plus the sum of CV and Rs times the logarithm of the ratio of V2 to V1. Similarly, if we substitute the expression obtained for the logarithm of the ratio of the final and initial specific volumes in the right-hand side of the equation of entropy production, then we can state that delta S is equal to the sum of CV and Rs times the logarithm of the ratio of T2 to T1, minus Rs times the logarithm of the ratio of P2 to P1. In the last step, we apply Meyer's relation for an ideal gas stating that the difference between the specific heat capacity Cp of the gas at constant pressure and its specific heat capacity Cv at constant volume is equal to its specific gas constant Rs. Since the heat capacity ratio gamma is defined by Cp over Cv, Rs over Cv is equal to gamma minus 1. If we substitute this expression in the equations in the left-hand side, we can summarize the change in the specific entropy of an ideal gas as follows. We saw that if the transformation of the state of an ideal gas consists of an isochoric process and an isothermal process, then the change delta S in the entropy over the specific heat capacity Cv of the gas at constant volume is equal to the natural logarithm of the ratio of the final temperature T2 of the gas to its initial temperature T1, plus the heat capacity ratio gamma plus 1 times the natural logarithm of the ratio of the final specific volume V2 of the gas to its initial specific volume V1. If the transformation of the state of an ideal gas consists of an isochoric process and an isobaric process, then delta S over Cv can be written as the natural logarithm of the ratio of the final pressure P2 of the gas to its initial pressure P1, plus gamma times the natural logarithm of the ratio of the specific volume V2 to the specific volume V1. Finally, if the transformation of the state of an ideal gas consists of an isobaric process and an isothermal process, delta S over Cv is given by gamma times the natural logarithm of the ratio of the temperature T2 to the temperature T1, plus 1 minus gamma times the natural logarithm of the ratio of the pressure P2 to the pressure P1. The entropy formula for an ideal gas also demonstrates the principle of entropy production in the experiment performed by Gay-Lussac and Joule studying the free expansion of air. We already discussed this experiment using an apparatus with two identical gas containers connected with a tube and placed in a calorimeter. In the initial state A, one of these containers is filled with air and the other one is evacuated. The state variables of the gas in its initial state are the volume V1, the pressure P1 and the temperature T1. If we open the valve separating the containers from each other, then the gas will expand and fill the evacuated container, reaching the final state B. The volume of the gas after expansion is denoted by V2, which is equal to 2 times its initial volume V1. The final pressure and temperature of the gas are denoted by P2 and T2 respectively. Since Joule was not able to measure any difference between the initial and the final temperature of the gas, that is T1 is equal to T2, the expansion of the air can be considered as an isothermal process. Then we can apply the first formula obtained for the change in entropy of an ideal gas, where the first term in the parenthesis vanishes because the temperature of the gas does not change. In the temperature-volume diagram, the isothermal free expansion of the air is represented by the horizontal line between its initial state A and its final state B. As a result, delta S is equal to the mass m of the gas times its specific gas constant Rs, times the natural logarithm of the ratio of the final volume V2 of the gas to its initial volume V1. We can also write the multiplicative factor of the logarithm as the amount of species n of the gas times the universal gas constant R. For a given amount of air measured in moles, the multiplicative factor is a positive constant. Since the gas doubles its volume by filling both the identical containers, the volumetric ratio V2 over V1 is equal to 2 and its logarithm is positive. The graph of the change in the entropy as a function of the volumetric ratio shows the entropy production represented by the logarithmic curve connecting the initial state A and the final state B. Since the logarithmic function is monotonic increasing, the entropy of the gas has maximum in the final state. Then the change in the entropy of the ideal gas during its free expansion is positive, that is, its entropy increases. We conclude that the free expansion of an ideal gas is an irreversible process since it involves entropy production. In other words, this process cannot take place in the reverse direction and the air filling both the vessels cannot contract spontaneously such that it would fill only one of the containers, since the volumetric ratio was less than 1, making the change in the entropy negative. That is, the entropy of the gas would decrease during its isothermal contraction, which will not happen in nature. We note that the change in entropy could be calculated along a quasi-static path for a reversible isothermal expansion since the entropy is a state function depending only on the initial and the final states of the gas, but not the path of the process. However, as the entropy production during the free expansion of the air shows that the process of itself is not reversible. Another example will help us to study the entropy production in the case of heating bodies or liquids. Let us heat a body at a constant pressure in a reversible process by allowing the body to always absorb a small amount of heat while it is warmed up. Such an idealized process can be approximated by simmering water in a pot. As opposed to boiling, simmering can be a much slower process where the water is warmed by a small amount of heat released from the oven in a unit time. This process is illustrated in the pressure-temperature diagram where the body is brought from its initial state A at the temperature T1 into its final state B at the temperature T2 while the pressure P is constant. Then the change in the entropy S of the body during its heating can be written as the integral of the reduced heat of the body from the temperature T1 to the temperature T2. Here the differential of the heat Q is equal to the mass m of the body, times the specific heat capacity Cp of the body for constant pressure, times the differential of its temperature T. By inserting this expression into the integral and performing the integration, we obtain m times Cp times the natural logarithm of the ratio of T2 to T1, provided the specific heat capacity can be approximated as a constant in the temperature range between T1 and T2. In the case of water, the specific heat for constant pressure has a very small change between the temperatures 0 degrees Celsius and 20 degrees Celsius. At 0 degree it is equal to 4.217 kJ per kilogram Kelvin, whereas at 20 degree it is given by 4.187 kJ per kilogram Kelvin. In linear approximation, its average in this temperature range is equal to 4.199 or about 4.2 kJ per kilogram Kelvin. If we heat 100 grams water from 0 degrees Celsius or 273.16 Kelvin to 20 degrees Celsius or 293.16 Kelvin, then the change in the entropy S of the water can be written as 0.1 kilogram times 4.2 kJ per kilogram Kelvin, times the natural logarithm of the ratio of 293.16 Kelvin to 273.16 Kelvin. This gives 29.67 Joule per Kelvin. That is, the increase in the entropy of 100 grams water is equal to about 30 Joule per Kelvin while it is heated from 0 degrees Celsius to 20 degrees Celsius. If we choose the entropy of 100 grams water at 0 degrees Celsius as the 0 point of the entropy of water, then we can state that the entropy of 100 grams water at 20 degrees Celsius is equal to about 30 Joule per Kelvin. Entropy production can also be studied in the case of mixing liquid at different temperatures. We have just determined the entropy S of 100 grams water at 20 degrees Celsius for a 0 point of 0 degrees Celsius, and we found that it is equal to 29.67 Joule per Kelvin. We can compute the entropy S of 50 grams water at 80 degrees Celsius by applying the same formula. Since the specific heat capacity Cp of water at 80 degrees Celsius is equal to 4.195 Joule per kilogram Kelvin, its approximation with the value of 4.2 still gives a relative accurate result when we substitute it into the formula of the entropy production. Then we can see that the entropy S of 50 grams water at 80 degrees Celsius is equal to 53.94 Joule per Kelvin for the same 0 point. Now we can determine the total entropy of the system, which consists of the two separated fluids. The total entropy S1 is the sum of the entropy of the two liquids, and after substituting their computed values in the sum, we obtain 83.61 Joule per Kelvin. If we mix these two separated fluids and measure the temperature of the mixture, we see that the 150 grams water has the temperature of 40 degrees Celsius. Then the entropy S2 of the mixture can be determined by applying the same formula and the same specific heat capacity Cp for the water at 80 degrees Celsius. This gives 86.09 Joule per Kelvin for the entropy S2. The difference between the entropy S2 of the mixture and the total entropy S1 of the separated fluids is equal to 2.45 Joule per Kelvin, which is greater than 0. This result shows that the mixing of water at two different temperatures increases the entropy of the isolated system consisting of the two fluids. The entropy production of this experiment demonstrates that mixing is an irreversible process, and its reverse does not take place spontaneously in nature. If we mix water at two different temperatures, then the mixture never separates into two different regions with different temperatures in a spontaneous process. In the last example illustrating entropy production, we study Carnot cycle. When this thermodynamic process was examined, we used the pressure-volume diagram of the process to analyze the four steps of the cycle along two isotherms represented by the red hyperbolas and two adiabats represented by the yellow curves. The diagram shows that the thermodynamic states A and B are connected with the isotherm at the temperature T1, whereas the states C and D are connected with the isotherm at the temperature T2. Similarly, the states A and D are connected with an adiabat, and the states B and C are connected with another adiabat. The four steps of Carnot cycle can be seen in this table, which are the processes transforming the thermodynamic system from the state A to the state B, from the state B to the state C, from the state C to the state D, and from the state D to the state A respectively. As the pressure-volume diagram shows, the first step of the cycle is an isothermal expansion of the working substance in the system at the temperature T1, where the initial volume VA of the substance is smaller than its final volume VB. Since this process is isothermal, the heat Q1 absorbed by the substance during its expansion is given by the product of the temperature T1 and the change in the entropy S of the system during the isothermal expansion. We already determined the later for an ideal gas, and we saw that the difference between the entropy S at the final state B and the initial state A of an isothermal expansion is equal to the mass m of the gas times its specific gas constant Rs, times the natural logarithm of the ratio of the final volume VB to the initial volume VA. As a result, the change in the entropy is positive in the first step of the cycle, that is, the isothermal expansion of the working substance involves entropy production in the system. The second step of the cycle is an adiabatic expansion between the states B and C, where no heat is exchanged between the working substance and its surroundings, and the initial volume VB of the system is smaller than its final volume VC. Since there is no heat absorbed or rejected by the system, there is no change in the entropy S of the working substance, and this step is an isentropic process. The third step of the cycle is an isothermal compression of the working substance at the temperature T2, where the initial volume Vc of the system is greater than its final volume Vd. In the isothermal compression of the working substance, the heat Q2' discarded by the system is given by the product of the temperature T2 and the change in the entropy S of the substance during this process. If we want to determine delta S for the isothermal compression, we can apply the same formula as in the first step. The only difference is that the initial volume of the system is Vc and its final volume is Vd. However, we also saw that the ratio of Vc to Vd is equal to the reciprocal of the ratio of Vb and Va in a Carnot cycle. The change in the entropy S is therefore given by minus the mass m times the specific gas constant Rs, times the logarithm of Va to Vb. In this case, the change in the entropy of the working substance is negative, and its magnitude is the same as the increase in the entropy in the first step. The fourth step of the cycle is an adiabatic compression between the states D and A, where no heat is exchanged between the working substance and its surroundings, and the initial volume Vd of the system is greater than its final volume Va. Since there is no heat absorbed or rejected by the system, there is no change in the entropy S of the working substance, and this step is an isentropic process. We can also study the heat transfer and the entropy production in a Carnot cycle by plotting the process variables in a temperature versus entropy diagram. In such a diagram, the isothermal expansion and compression of the working substance are represented by the horizontal lines between the states A and B, and the states C and D at the temperatures T1 and T2 respectively. Similarly, the vertical lines between the states B and C, and the states D and A at SA and SB represent the adiabatic expansion and compression of the working substance, which are isentroptic processes. The heat Q1 absorbed by the working substance during its isothermal expansion is given by the area of the rectangle with the corners A, B, E and F. The heat Q2' rejected by the working substance during its isothermal compression is given by the area of the rectangle with the corners D, C, E and F. Since the work W' delivered in the Carnot cycle is equal to the difference between the absorbed heat Q1 and the rejected heat Q2', the area of the rectangle with the corners A, B, C and D in the temperature entropy diagram gives W'. As a result, the thermal efficiency eta of the Carnot cycle defined by the ratio of the work W' delivered by the system to the heat Q1 absorbed by the system, is equal to the ratio of the area of the rectangle A, B, C and D to the area of the rectangle A, B, E and F. In the temperature versus entropy diagram, we can see that the greater the difference between the temperature T1 of the heat source and the temperature T2 of the cold sink is, the greater the ratio of the rectangular areas and the formula of the efficiency becomes. In other words, this diagram illustrates the fact that the efficiency eta is given by the ratio of T1 minus T2 to T1. We have already introduced three state functions describing the state of thermodynamic systems: the internal energy, enthalpy, and entropy of a system. The state functions, also called thermodynamic potentials, are completely determined by the state P of a thermodynamic system, that is, they are unique functions of the state variables x1, x2, ellipsis, xn describing the state of the system, as seen here in the case of the internal energy U. If the system is brought from an initial state P0 to the state P during a thermodynamic process along a path calligraphic P in the state space, then the change in its state functions, for example the change in its internal energy U, depends only on the initial and final states of the process, and is independent of the path calligraphic P. In other words, the infinitesimal change in the state functions is an exact differential, that is, the differential of U is exact. Besides internal energy, entropy, and enthalpy, there are two other state functions in thermodynamics providing more information on the state of a system. The first one is introduced by Helmholtz, and it is called Helmholtz free energy. In order to define free energy, we write the first law of thermodynamics in a differential form, stating that the infinitesimal change in the internal energy U of a system is equal to the sum of the infinitesimal amount of heat Q exchanged between the system and its surroundings and the infinitesimal amount of work W done during the heat exchange. When we talk about the expansion or the contraction of the volume of the system, as in the case of an ideal gas warmed up or cooled down, we can write the infinitesimal work as the pressure volume work given by minus the pressure P of the gas times the infinitesimal change in the volume V of the gas. The second law of thermodynamics states that the infinitesimal amount of heat Q exchanged between the system and its surroundings is less than or equal to the temperature T of the system times the infinitesimal change in its entropy S, depending on whether the process of the heat transfer is irreversible or reversible. If we substitute the second law in the first one, we can write that the differential of the internal energy U is less than or equal to the temperature T times the differential of the entropy S, plus the infinitesimal amount of work W, or T times ds minus the pressure P times the differential of the volume V. In the case of an isothermal process, the temperature T of the system is constant, and the differentials can formally be factored out from the difference between du and T times ds if we reorder the terms in the inequality. As a result, the differential of the difference between the internal energy U and the product of the temperature T and the entropy S is less than or equal to the infinitesimal work W, or minus the pressure P times the differential of the volume V. Helmholtz used the expression in the parenthesis, that is the internal energy U minus the product of the absolute temperature T and the entropy S, when he defined a new state function called free energy F in 1883. By virtue of the first law, we already decomposed the internal energy U of a thermodynamic system to the sum of the heat Q transferred to or from the system, and the work W done on the system. The choice of the name free energy indicates that the internal energy U of a thermodynamic system can also be interpreted as the sum of the free energy F, and the bound energy of the system given by the product of its temperature T and entropy S. Now we will explain why free energy can be considered as a free form of energy, and why the product of the temperature and the entropy represents a bound form of it. We saw that the differential of the internal energy U minus the temperature T times the entropy S is less than or equal to the infinitesimal amount of work W done on the system. By applying the definition of free energy, we can state that the production of the free energy F given by its differential is less than or equal to the infinitesimal work W done on the system. The latter is equal to minus the infinitesimal work W prime done by the system, as seen in the figure with the sign convention for the direction of the energy transfer in the form of heat and work between a thermodynamic system and its surroundings. Then we can state that the infinitesimal decrease in the free energy F is greater than or equal to the infinitesimal work W prime done by the system. This inequality can also be written with finite differences stating that the decrease in the free energy F of the system brought from the state 1 to the state 2 is greater than or equal to the work W prime done by the system. As a result, the maximum infinitesimal work W prime done by the system is equal to the negative infinitesimal change in the free energy F of the system. In other words, the decrease in the free energy of a thermodynamic system measures the maximum work that can be done by the system during an isothermal process in a reversible limit. By virtue of the first law, the infinitesimal decrease in the total internal energy U is given by minus the infinitesimal amount of heat Q absorbed by the system, minus the infinitesimal amount of work W done on the system. As the figure shows, minus the heat Q absorbed by the system is equal to the heat Q prime discarded by the system, and minus the work W done on the system is equal to the work W prime done by the system. At the same time, we can use the definition of free energy and write the infinitesimal decrease in internal energy U as minus the differential of the sum of the free energy F and the product of the temperature T and the entropy S, which is equal to minus the differential of the free energy F, minus the differential of the product of the temperature T and the entropy S. By eliminating the differential of the internal energy U from these two expressions, we obtain an equation stating that sum of dq prime and dw prime is equal to minus df minus the differential of the product of T times S. We already saw that minus the differential of the free energy F is greater than or equal to the infinitesimal work W prime. Then it follows from this inequality in the equation that minus the differential of the product of the absolute temperature T of a system and its entropy S must be less than or equal to the infinitesimal amount of heat Q prime discarded by the system. This result shows that in an isothermal process, the free energy of the system is the maximum amount of energy from its total internal energy which can be converted to useful work. The rest of the internal energy represented by the bound energy of the system, that is the product of its temperature and its entropy, is minimally released in the form of heat by the system. As an example, we will determine the free energy of an ideal gas in a final state of a thermodynamic process. A given amount of gas can expand from an initial state A with the temperature T0 and the volume V0 to a state B with the temperature T and the volume V, by absorbing some heat Q from its surroundings while doing some work W prime on it. We already derived the entropy production in a transformation between the states A and B, and we found that it is equal to the mass m of the gas times the sum of the heat capacity CV of the gas at constant volume times the natural logarithm of the ratio of T to T0, and the specific heat capacity Rs of the gas times the natural logarithm of the ratio of V to V0. We can choose the initial state A as a zero state, where the entropy S of the gas is set to 0. We also note that the internal energy U of an ideal gas is given by its mass m times its specific heat capacity CV times its absolute temperature T. The expressions of entropy and internal energy can be substituted in the free energy F of the gas defined by its internal energy U, minus the product of its temperature T and entropy S. Then we can write that F is equal to the mass m of the gas, times the quantity of the specific heat capacity CV of the gas times its temperature T, minus the specific heat capacity CV of the gas times its temperature T times the natural logarithm of the ratio of the temperature T to the temperature T0, minus its specific gas constant Rs times the temperature T times the natural logarithm of the ratio of the volume V of the gas to the volume V0 of the gas at the temperature T0. If the gas undergoes an isothermal expansion, that is, it increases its volume from V0 to V at a constant temperature, then the decrease in the free energy of the gas is equal to its mass m times its specific gas constant Rs times its constant temperature T, times the natural logarithm of the ratio of the volume V to the volume V0. The product m times Rs can also be written as the amount of species n of the gas times the universal gas constant R, and the whole expression is equal to the work W' of an expanding ideal gas in a reversible process, as we expected. We already saw that the entropy in an isolated system increases during irreversible processes in nature. Since there is no exchange of energy in the form of heat or work between an isolated system and its surrounding, there is no change in the internal energy of such a system either. Then the statement on the entropy production in an isolated system immediately follows from the combined form of the first and the second laws of thermodynamics, stating that the differential of the internal energy U of the system is less than or equal to its absolute temperature T times the differential of its entropy S, plus the infinitesimal work W done on the system. This inequality reduces to the one stating that T times ds is greater than or equal to 0 because both du and dw vanish for an isolated system. Since the absolute temperature T is non-negative, the differential of the entropy S of an isolated system is greater than or equal to 0. In the case of non-isolated systems, the exchange of energy is allowed between the system and its surroundings, at least in the form of heat. We introduced free energy for isothermal processes, and now we suppose the process is isochoric as well. Then the infinitesimal change in both the temperature T and the volume V of the system vanishes. We can apply the inequality obtained for the decrease of the free energy in the form stating that the differential of the free energy F is less than or equal to the infinitesimal work W' done by the system. The latter represents the pressure volume work given by the product of the pressure P of the working substance and the infinitesimal change in its volume V. Since dV is 0, we can write that the differential of the free energy F is less than or equal to 0. Then we conclude that in an isothermal and isochoric process, the Helmholtz free energy of a thermodynamic system decreases until the system reaches equilibrium, and the free energy attains its minimum. In other words, thermodynamic processes in a system minimize its free energy under constant temperature and constant volume. The last state function introduced by Gibbs is called free enthalpy or Gibbs potential, and its definition is analogous with the one of free energy in a thermodynamic system with a given internal energy U and entropy S. We already used the combined formula of the first and second laws of thermodynamics, stating that the differential of the internal energy U is less than or equal to the temperature T of the system times the differential of the entropy S plus the infinitesimal work W done on the system. Here the infinitesimal amount of heat Q absorbed by the system is less than or equal to T times ds due to the second law. We usually consider the work W as the pressure volume work given by minus the pressure P of the system times the differential of its volume V, but now we include the infinitesimal work associated with some chemical potential, or done by electromagnetic or other external forces. For the sake of brevity, let Wx denote the net work done by all these various types of forces. If we reorder the inequality, we can write that the differential of the internal energy U, plus the pressure P times the differential of the volume V, minus the temperature T times the differential of the entropy S is less than or equal to the infinitesimal work Wx done by the various types of forces. For isothermal and isobaric processes, the differentials of the temperature T and the pressure P vanish. Since the pressure P is constant during the process, the pressure P times the differential of the volume V can be written as the differential of the product of the pressure P and the volume V. Then the differential can be factored out from the left-hand side of the inequality, and we can state that the differential of the three terms, that is the internal energy U, plus the pressure P times the volume V, minus the temperature T times the entropy S is less than or equal to the infinitesimal work Wx. Here the sum of the internal energy U and the product of the pressure P and the volume V is defined as the enthalpy H of the system, and the left-hand side of the inequality can be written as the differential of the difference between the enthalpy H and the product of the temperature T and the entropy S. We have already shown that the product of the temperature and the entropy represents a bound energy stored in a thermodynamic system, which motivated Helmholtz to define free energy. Similarly, in the early 1870s, Gibbs introduced another thermodynamic potential or state function called free enthalpy or Gibbs potential. The free enthalpy G is defined by the enthalpy H minus the product of the temperature T and the entropy S. This definition can also be written as the internal energy U, plus the pressure P times the volume V, minus the temperature T times the entropy S. It follows from the definition that the SI unit of the free enthalpy G is joule, that is, it has a dimension of energy. This thermodynamic potential is also known as Gibbs free energy, but we will use the phrase free enthalpy to avoid its confusion with Helmholtz free energy, which we simply call free energy. As in the case of the internal energy U, the introduction of a free quantity allows us to decompose the enthalpy H in two different ways. On the one hand, the enthalpy H is defined by the sum of the internal energy U and the product of the pressure P and the volume V. On the other hand, the enthalpy H can be written as the sum of the free enthalpy G and the product of the temperature T and the entropy S, which plays the role of the bound form of the enthalpy now. By applying the definition of free enthalpy, we can write the original inequality as the one stating that the differential of the free enthalpy G is less than or equal to the infinitesimal work Wx done on the system by the various types of forces. The latter is equal to the work W'x done against these forces by the system, and we find that the negative infinitesimal change in the free enthalpy G of the system is greater than or equal to the infinitesimal work W'x done by the system. As a result, the maximum amount of work Wx' done by the system is equal to the decrease in the free enthalpy G of the system. In other words, the decrease in the free enthalpy of a thermodynamic system measures the maximum work apart from the pressure volume work that can be done by the system on its surroundings during an isothermal and isobaric process in a reversible limit. If there are no chemical reactions in the system or no electromagnetic or external forces act on it, then the work minus dW'x vanishes and the infinitesimal change in the free enthalpy G is less than or equal to zero. Then we conclude that in an isothermal and isobaric process, the free enthalpy of a thermodynamic system decreases until the system reaches equilibrium, and the free enthalpy attains its minimum. In other words, thermodynamic processes in a system minimize its free enthalpy or Gibbs potential under constant temperature and constant pressure. We have already introduced several thermodynamic potentials that can be summarized here. A thermodynamic system with a specified set of state variables has a given internal energy U and entropy S. If we focus on ideal gases, the variables describing the state of the system are the pressure P, the volume V and the absolute temperature T of the gas. A thermodynamic process transforms the state of the system from one state to another one while the system may exchange energy with its surrounding in the form of the heat Q and the work W. Thermodynamic potentials also describe the state of such a system, and their change can characterize the nature of the processes transforming the state of the system. This table shows the 5 thermodynamic potentials already defined in the lecture. In the first 2 rows we can see the internal energy U and the entropy S of a system. The enthalpy H of a thermodynamic system is defined by the sum of its internal energy U and the product of the pressure P and the volume V. The Helmholtz free energy or simply the free energy F of a thermodynamic system is defined by the difference between its internal energy U and the product of its temperature T and entropy S. The free enthalpy or the Gibbs potential G of a thermodynamic system is defined by the difference between its enthalpy H and the product of its temperature T and entropy S, which is equal to the internal energy U, plus the pressure P times the volume V, minus the temperature T times the entropy S. The relationships between the different thermodynamic potentials are illustrated in this figure. Here we represent the potentials and the products P times V and T times V by different bars arranged in 4 lines. If we compare the first line with the second one, then we obtain the definition of the enthalpy H, while its comparison with the third line gives the enthalpy in terms of free energy and entropy. Similarly, in the second and third lines we can see the decomposition of the internal energy U into the bound energy T times S and the free energy F. The first and the last lines also show that the enthalpy H is the sum of the bound energy T times S and the free enthalpy G. By comparing each line with another one, we can express any of the thermodynamic potentials in terms of the rest of the potentials. As the name of the thermodynamic potentials indicates, these 5 quantities are state functions. In the state space with the state variables x1, x2, ellipsis, xn of a thermodynamic system, the state of the system can be represented by a point P in the state space. Then each potential are evaluated at the point P. That is, any thermodynamic potential phi I is a unique function of the state variables x1, x2, ellipsis, xn, where phi I denotes the internal energy U, the entropy S, the enthalpy H, the free energy F and the free enthalpy G. As already mentioned, the state variables of an ideal gas are always the pressure P, the volume V, and the temperature T of the gas. In a more general treatment of thermodynamic systems, the amount of the working substance is not fixed, and its mass, the amount of species or the number of gas particles, also becomes a state variable. Here we use the number of particles Ni to describe the amount of the substance in the thermodynamic system. The index I denotes the different species in a multi-component systems with more than one type of species. The variables xk represent the state variables associated with external forces acting on the system, such as gravitational or electromagnetic forces. Since each thermodynamic potential phi I is a state function, its change between any point p0 and the point p in the state space only depends on the initial and final states of the system, and is independent of the path calligraphic p of the process between these two states. In other words, the differential of any potential phi I is an exact differential, and it can be expressed as the sum of the partial derivative of the potential with respect to each state variable, times the differential of the corresponding state variable. When we introduced the 5 thermodynamic potentials, we also studied the extremum principle stating that these potentials change during a thermodynamic processes in an isolated system such that they reach extrema at equilibrium. Since this principle follows from the first and second laws of thermodynamics, we will apply them to present the quantitative analysis of thermodynamic equilibrium. The first law of thermodynamics states that the infinitesimal change in the internal energy U of a system is equal to the sum of the infinitesimal amount of heat Q absorbed by the system, and the infinitesimal work W done on the system during the process. By applying the second law, we can see that the sum in the right-hand side is less than or equal to the temperature T of the system times the differential of its entropy S, plus the infinitesimal work given by minus the pressure P of the system times the differential of its volume V. Here we assume that only the pressure volume work is done in the process and no external forces act on the system. Then we obtain our first inequality stating that the differential of the internal energy U is less than or equal to the temperature T times the differential of the entropy S, minus the pressure P times the volume V. We can also write this inequality in the form where the differential of the entropy S is greater than or equal to 1 over the temperature T times the differential of the internal energy U, plus the pressure P over the temperature T times the differential of the volume V. These two inequalities are therefore equivalent. Now we can use the definition of the enthalpy H to write its differential as the differential of the sum of the internal energy U and the product of the pressure P and the volume V. By factoring out the terms in the parentheses and substituting the first inequality into the differential of the internal energy U, we can write that dH is less than or equal to the temperature T times the differential of the entropy S minus the pressure P times the differential of the volume V, plus the differential of the product of the pressure P and volume V given by V times dP plus P times dV. Then we obtain T times ds plus V times dP. As a result, our third inequality tells us that the differential of the enthalpy H is less than or equal to the temperature T times the differential of the entropy S, plus the volume V times the differential of the pressure P. We also derive the differential of the free energy F in the same way. By applying its definition, we can write dF as the differential of the difference between the internal energy U and the product of the temperature T and the entropy S. If we factor out the terms in the parentheses and substitute the first inequality into the differential of the internal energy U, then we obtain an inequality stating that dF is less than or equal to T times ds minus P times dV, minus the differential of the product of T and S given by the sum of S times dt and T times ds. Since the right-hand side can be reduced to minus S times dt minus P times dV, our fourth inequality states that the differential of the free energy F is less than or equal to minus the entropy S times the differential of the temperature T, minus the pressure P times the differential of the volume V. Similarly, the fifth inequality for the differential of the free enthalpy G can be obtained from the differential of the difference between the enthalpy H and the product of the temperature T and the entropy S. By factoring out the terms in the parentheses and substituting the third inequality into the differential of the enthalpy H, we can write that dG is less than or equal to T times ds plus V times dP, minus the differential of T times S given by the sum of S times dt and T times ds. Then we obtain minus S times dt plus V times dP, and the final inequality states that the differential of the free enthalpy G is less than or equal to minus the entropy S times the differential of the temperature T, plus the volume V times the differential of the pressure P. In these inequalities the differentials of the 5 thermodynamic potentials appear in the left-hand side, whereas some linear combinations of the differentials of the potentials and the state variables can be seen in the right-hand side. The potentials and variables appearing in the differentials are called the natural variables of the potential in the left-hand side of the inequalities. In this table, we display the pair of the natural variables for each thermodynamic potential. The natural variables of the internal energy U are the entropy S and the volume V, as seen in the first inequality. The second inequality shows that the natural variables of the entropy S are the internal energy U and the volume V. The natural variables of the enthalpy H are the entropy S and the pressure P, as seen in the third inequality. This table shows that one of the natural variables of internal energy, entropy and enthalpy, is a thermodynamic potential, and the other one is a state variable. It is not the case for free energy and free enthalpy, where the natural variables are only state variables. For the free energy F, the natural variable pair is the temperature T and the volume V, and the natural variables of the free enthalpy G are the temperature T and the pressure P, as seen in the last two inequalities. The extremum principles related to the thermodynamic potentials, stating that each potential has an extremum in thermodynamic equilibrium, are derived from the laws of thermodynamics. Then these extrema can simply be determined from the inequalities based on the same laws if the natural variables of the potentials are held constant, that is, when their differentials are equal to zero. Then the right-hand side of the inequalities vanish and we conclude the following. In an isentropic and isochoric process, the infinitesimal change in the internal energy U of a system is less than or equal to zero. The internal energy of the system decreases during the process, and it has a minimum when the system reaches equilibrium. In an isochoric process, where the internal energy of the system is also constant, the infinitesimal change in the entropy S of the system is greater than or equal to zero. The entropy of the system increases during the process, and it has a maximum when the system reaches equilibrium. In an isentropic and isobaric process, the infinitesimal change in the enthalpy H of a system is less than or equal to zero. The enthalpy of the system decreases during the process, and it has a minimum when the system reaches equilibrium. In an isothermal and isochoric process, the infinitesimal change in the free energy F of a system is less than or equal to zero. The free energy of the system decreases during the process, and it has a minimum when the system reaches equilibrium. In an isothermal and isobaric process, the infinitesimal change in the free enthalpy G of a system is less than or equal to zero. The free enthalpy of the system decreases during the process, and it has a minimum when the system reaches equilibrium. We already presented these extremum principles for each potential, and we have only shown now that they directly follow from the set of inequalities derived here. The extremum principles of course hold for general thermodynamic processes as well, and they simultaneously hold for each potential in a given process. We illustrate this fact by plotting the functional relation between the internal energy U, the entropy S, and the volume V of a thermodynamic system. This functional relation is represented by a surface in the three-dimensional subspace of the state space, where the surface is restricted to only one quadrant in the coordinate system for the sake of simplicity. We can illustrate an isentropic process by cutting this surface with a plane of constant entropy, where the intersection of the surface and the plane defines a curve along which the internal energy changes. At the point P, the internal energy has a minimum and it represents an equilibrium point of the system. If we cut the surface with the plane of constant internal energy such that their intersection passes through the point P, we can see another curve along which the entropy changes and it has a maximum at the equilibrium point P. This shows that the system has minimum internal energy and maximum entropy in its thermodynamic equilibrium. In a general thermodynamic process with the equilibrium point P, the curve representing the change both in the internal energy and the entropy of the system passes through the point P, such that the internal energy decreases and the entropy increases simultaneously along the curve. Similar plots can also be created for including all the thermodynamic potentials as illustrations of the extremum principles. In order to derive the fundamental equations or relations of thermodynamics, we only need the 5 inequalities describing the infinitesimal change in the thermodynamic potentials during quasi-static processes. If these processes are reversible, then the inequalities become equalities, whereas the strict inequalities hold for irreversible processes. In other words, these inequalities are evaluated along a path of the process in the state space of a system, where the right-hand sides of the inequalities depend on this path. However, thermodynamic potentials are state functions, and their infinitesimal changes in the left-hand sides of the inequalities are exact differentials. As a result, they depend only on the initial and final states of the system in the infinitesimal process. These differentials measuring the infinitesimal change in the potentials between two states give the extrema of the right-hand side of the inequalities, as the irreversible path of a process connecting the two states approaches a reversible path. As a result, when the inequalities become equalities in the reversible limit, we can interpret them as the equations evaluated in the initial and final states of an infinitesimal process. The general description of infinitesimal changes in the thermodynamic potentials includes the change due to chemical reactions or the work done on the system by external forces. Here we only consider the contribution of chemical reactions because the change in the numbers of particles Ni in a multi-component system depends on these reactions. In order to describe chemical reactions in a thermodynamic system, we define the chemical potential μI associated with the species I in the system by the partial derivative of the potential phi j with respect to the number of particles Ni for the species I at a fixed set of potentials and state variables under a given condition. In other words, chemical potential measures the change in any thermodynamic potential under given conditions per the number of particles. Here the given condition represents a set of potentials and state variables determined by the potential phi j are held constant during the change in the number of particles. By taking chemical reactions into account, we can generalize the 5 equations that are known as the fundamental equations or relations in thermodynamics. The first one states that the differential of the internal energy U is equal to the temperature T times the differential of the enthalpy S, minus the pressure P times the differential of the volume V, plus the sum of the chemical potential μI times the differential of the number of particles Ni with the index I running over all the species in the system. If we solve this equation for the differential of the entropy S, then we obtain 1 over the temperature T times the differential of the internal energy U, plus the pressure P over the temperature T times the differential of the volume V, minus 1 over the temperature T times the sum of the chemical potential μI times the differential of the number of particles Ni. The third relation tells us that the differential of the enthalpy H is given by the temperature T times the differential of the enthalpy S, plus the volume V times the differential of the pressure P, plus the sum of the chemical potential μI times the differential of the number of particles Ni. The next relation is for the free energy F and states that its differential is equal minus the enthalpy S times the differential of the temperature T, minus the pressure P times the differential of the volume V, plus the sum of the chemical potential μI times the differential of the number of particles Ni. Finally, the differential of the free enthalpy G is given by minus the enthalpy S times the differential of the temperature T, plus the volume V times the differential of the pressure P, plus the sum of the chemical potential μI times the differential of the number of particles Ni. As already seen, the first 2 equations are equivalent and we have 4 independent fundamental relations describing infinitesimal changes in the 5 thermodynamic potentials. This figure shows the relationships between the different terms in the fundamental equations excluding the terms with chemical potentials. We represent the terms in the relations by different bars arranged in 4 lines. The first fundamental relation can be constructed from the left-hand side of the second and third lines indicating that T times ds is equal to the sum of du and P times dv. Similarly, the first 2 lines in the figure shows that dH is given by the sum of T times ds and V times dP. We can construct all of the fundamental relations for the thermodynamic potentials from this figure by adding the sum with the chemical potential to the result. Obviously, the second fundamental equation, where the factor of this sum is minus 1 over T, follows from the first relation with the positive sum. By introducing the contribution of chemical reactions to the change in thermodynamic potentials, we have increased the natural pairs of the potentials to 3. Here we can see the thermodynamic potentials as functions of their natural variables. For the internal energy U, the natural variables are the entropy S, the volume V and the number of particles Ni. In the case of the entropy S, this functional relation is inverted, and the natural variables are the internal energy U, the volume V and the number of particles Ni. For the enthalpy H, these variables are the entropy S, the pressure P and the number of particles Ni. Finally, the natural triplet for the free energy F is the temperature T, the volume V and the number of particles Ni, whereas this triplet consists of the temperature T, the pressure P and the number of particles Ni for the free enthalpy G. These natural triplets have a crucial role when we express a given thermodynamic potential as a function of another potential and the state variables. We can apply the fundamental equations of thermodynamics to give a quantitative analysis of the conditions for thermodynamic equilibrium. Let us consider a thermodynamic system separated into 2 subsystems with a wall. We assume that the system is isolated from its surroundings with a boundary which is an adiabatic, fixed and impermeable wall preventing the exchange of any heat, momentum for pressure work, and matter. We also assume that no external forces act on the system. These conditions have the mathematical expression stating that the differential of the heat Q transferred across the boundary wall, the pressure work W done on the system, and the mass m of the substance flowing across the wall vanish. As a result, we have 2 subsystems isolated from their surroundings by the boundary wall that can interact with each other depending on the properties of the separation wall. The state variables and functions describing the states of the interacting subsystems are labeled with the numbers 1 and 2. Then we can write that the total internal energy U of the system given by the sum of the internal energies U1 and U2 of the individual subsystems is constant. Similarly, the total volume V of the system given by the sum of the volumes V1 and V2 of the subsystems is constant, and the total number of the particles n in the system given by the sum of the number of particles n1 and n2 in the corresponding subsystems is also constant. In such a setup, the total entropy S of the system is equal to the sum of the entropies S1 and S2 of the individual subsystems written as functions of the internal energies, volumes, and numbers of particles of the subsystems. In order to examine the conditions of thermodynamic equilibrium in the whole system for different types of the separation wall, we will apply the second fundamental equation expressing the differential of the entropy S as 1 over the temperature T times the differential of the internal energy U, plus the pressure P over the temperature T times the differential of the volume V, minus 1 over the temperature T times the sum of the chemical potential mu I times the differential of the number of particles Ni. This equation can be used to determine the change in the entropies S1 and S2 of the subsystems during any process leading to equilibrium. First, we discuss the condition for thermal equilibrium where the average heat flux vanishes in the whole system. We assume that the initial temperatures T1 and T2 of the subsystems are different, and there is a net heat flux between the subsystems during their thermalization. Such a condition can be examined if the wall separating its two subsystems from each other is diathermal, fixed, and impermeable. A diathermal wall allows heat flux between the two subsystems, and any infinitesimal change in the internal energy U1 of the first subsystem is equal to minus the infinitesimal change in the internal energy U2 of the second subsystem as the total internal energy of the system is conversed. Since the wall is fixed and impermeable, the differentials of volumes V1 and V2, and the numbers of particles N1 and N2 vanish. If we suppose that the temperature T1 is greater than the temperature T2, then the net heat flows from the warmer subsystem to the colder one. That is, the change in the internal energy U1 of the warmer subsystem is negative, whereas the change in the internal energy U2 of the colder one is positive. During the thermalization of the system, its entropy S increases and reaches its maximum at equilibrium. Then the condition for thermodynamic equilibrium is that the differential of the entropy S of the isolated system vanishes. Since the total entropy is the sum of the entropies of the subsystems, ds is equal to the sum of the differentials of the entropies S1 and S2. By applying the fundamental relation for each subsystem and taking into account that the differentials of their volumes V1 and V2, and their numbers of particles N1 and N2 vanish, we can write that the sum is equal to 1 over the temperature T1 of the first subsystem times the differential of its internal energy U1, plus 1 over the temperature T2 of the second subsystem times the differential of its internal energy U2. We can eliminate one of the differentials from the right-hand side because the differential of U1 is equal to minus the differential of U2. As a result, ds is equal to the difference between 1 over T1 and 1 over T2, times du1. In thermodynamic equilibrium, the differential of the entropy S vanishes for arbitrary values for du1, and the terms in the parenthesis must be 0. Then the temperatures T1 and T2 are equal, showing the thermodynamic equilibrium at the end of the thermalization of the system is a thermal equilibrium. Now we conclude that the condition for thermal equilibrium in the whole system is that its two subsystems must have the same temperature. Although we established this criterion when we introduced the concept of heat in thermodynamics, here we formally derived it from the fundamental equation and the extremum principle for entropy. We can also illustrate how the extremum principle determines the direction of the thermalization taking place in the system. The principle tells us that the entropy S increases during the process, and its differential must be positive. Since we suppose that the temperature T1 is greater than the temperature T2, it follows from the last line in the equation chain of the vanishing differential of entropy that the infinitesimal change of the internal energy U1 of the warmer system is negative, as we have already shown it. Conversely, if the temperature T1 is less than the temperature T2, then the equation for thermal equilibrium shows that the differential of the internal energy U1 must be positive, that is, the net heat must flow from the warmer second subsystem to the colder first one, increasing the internal energy of the colder subsystem. Now we examine the condition of another type of equilibrium in the system called mechanical equilibrium. In this case, we assume that the wall separating the two subsystems from each other is diathermal, movable and impermeable. Then the heat flow is still allowed between the two subsystems, and the differential of the internal energy U1 is equal to minus the differential of the internal energy U2. Since the movable wall allows the change in the volumes V1 and V2 of the subsystems, we can state that the differential of the volume V1 is equal to minus the differential of the volume V2. For the impermeable wall, the differentials of the numbers of particles N1 and N2 vanish. If the system reaches thermodynamic equilibrium, then the differential of its entropy S, that is the sum of the differentials of the entropies S1 and S2 of the subsystems, vanishes. By applying the fundamental equation, We can write this sum as 1 over the temperature T1 times the differential of the internal energy U1, plus the pressure P1 over the temperature T1 times the differential of the volume V1, plus 1 over the temperature T2 times the differential of the internal energy U2, plus the pressure P2 over the temperature T2 times the differential of the volume V2. Since dU1 is equal to minus dU2 and dV1 is equal to minus dV2, we can express ds as the difference between 1 over T1 and 1 over T2 times dU1, plus the difference between P1 over T1 and P2 over T2 times dV1. As the expression must vanish for arbitrary and independent values of dU1 and dV1, the terms in both parentheses must individually vanish, that is 1 over T1 minus 1 over T2 is equal to 0, and P1 over T1 minus P2 over T2 is equal to 0. Then we conclude that the temperature T1 is equal to the temperature T2, and the pressure P1 is equal to the pressure P2. The equality of the temperatures, that is the thermal equilibrium in the system, is just the consequence of the diathermal property of the wall separating the two subsystems from each other. The equality of the pressures in the two subsystems is the result of motion of the wall balancing the pressure forces acting from both the sides of the wall. If the pressure is initially different in the two subsystems, then the net pressure force acting on the wall moves it, such that the pressure will be equalized in the whole system as the result of the changing volumes of the subsystems. Since the pressure produces mechanical forces exerted on the wall, the balance of forces involves that the system is in mechanical equilibrium. Now we examine the condition for a third type of equilibrium in the system called chemical equilibrium. Such a condition can be examined if the wall separating the two subsystems from each other is diathermal, fixed and permeable. For a diathermal wall, any infinitesimal change in the internal energy U1 is equal to minus the infinitesimal change in the internal energy U2 due to the heat flow across the wall. Since the wall is fixed, the differentials of volumes V1 and V2 vanish. For a permeable wall allowing the exchange of the matter between the two subsystems within the isolated system, we can write that the differential of the number of particles N1 is equal to minus the differential of the number of particles N2. We can start again with the vanishing differential of the entropy S of the system as the general criterion of its thermodynamic equilibrium, which is equal to the sum of the differentials of the entropies S1 and S2 of the subsystems. By applying the fundamental equation, we can write this sum as 1 over the temperature T1 times the differential of the internal energy U1, minus the chemical potential mu1 over the temperature T1 times the differential of the number of the particles N1, plus 1 over the temperature T2 times the differential of the internal energy U2, minus the chemical potential mu2 over the temperature T2 times the differential of the number of particles N2. Since dU1 is equal to minus dU2 and dN1 is equal to minus dN2, we can express ds as the difference between 1 over T1 and 1 over T2 times dU1, minus the difference between mu1 over T1 and mu2 over T2 times dN1. As the expression must vanish for arbitrary and independent values of dU1 and dN1, the terms in both parentheses must individually vanish, that is 1 over T1 minus 1 over T2 is equal to 0, and mu1 over T1 minus mu2 over T2 is equal to 0. Then we conclude that the temperature T1 is equal to the temperature T2, and the chemical potential mu1 is equal to the chemical potential mu2. Since the wall of separation is diathermal and the heat flux across the wall can thermalize the two subsystems, we have obtained the criterion of thermal equilibrium again. At the same time, the wall is also permeable, allowing matter flow between the two subsystems. The second criterion tells us if the chemical potential is different in the two subsystems, then this difference produces a generalized force for matter flow. As a result, some amount of matter is exchanged between the two subsystems till their chemical potentials become equal and the system reaches chemical equilibrium. Now we determine some of the thermodynamic variables and potentials as the derivatives of the potentials at given conditions during a process in a thermodynamic system. We have seen that each fundamental equation describes the differential of a given thermodynamic potential as a function of other potentials and state variables. We called the quantities appearing in the differentials in the right-hand sides of these four equations the natural variables of the potential in the left-hand sides. If we express the potentials as functions of their natural variables, then their exact differentials can also be written as the sum of the partial derivatives of the potentials with respect to the natural variables times the differentials of the natural variables. The first fundamental equation shows that the natural variables of the internal energy U are the entropy S, the volume V and the number of particles Ni. Then the differential of the internal energy U is equal to the partial derivative of U with respect to S at constant V and Ni, times the differential of S, plus the partial derivative of U with respect to V at constant S and Ni, times the differential of V, plus the sum of the partial derivative of U with respect to Ni at constant S, V, and Nj, where j is not equal to I, times the differential of Ni. Here the index I runs through all the species in the system. By considering the second fundamental equation, we see that the natural variables of the enthalpy H are the entropy S, the pressure P and the number of particles Ni. As a result, the differential of the enthalpy H can be written as the partial derivative of H with respect to S at constant P and Ni, times the differential of S, plus the partial derivative of H with respect to P at constant S and Ni, times the differential of P, plus the sum of the partial derivative of H with respect to Ni at constant S, P and Nj where j is not equal to I, times the differential of Ni. The third fundamental equation shows that the natural variables of the free energy F are the temperature T, the volume V and the number of particles Ni. Then the differential of the free energy F is equal to the partial derivative of F with respect to T at constant V and Ni, times the differential of T, plus the partial derivative of F with respect to V at constant T and Ni, times the differential of V, plus the sum of the partial derivative of F with respect to Ni at constant T, V and Nj where j is not equal to I, times the differential of Ni. Finally, it follows from the fourth fundamental equation that the natural variables of the free enthalpy G are the temperature T, the pressure P and the number of particles Ni. The differential of the free enthalpy G is therefore given by the partial derivative of G with respect to T at constant P and Ni, times the differential of T, plus the partial derivative of G with respect to P at constant T and Ni, times the differential of P, plus the sum of the partial derivative of G with respect to Ni at constant T, P and Nj where j is not equal to I, times the differential of Ni. By comparing the equations in the left and the right-hand side in each line we find the following. The comparison of the equations in the first line gives three expressions, where the first one states that the temperature T is equal to the partial derivative of the internal energy U with respect to the entropy S at the constant volume V and the number of particles Ni. The second one tells us that the pressure P is given by minus the partial derivative of the internal energy U with respect to the volume V at the constant entropy S and the number of particles Ni. The third one states that the chemical potential μI is equal to the partial derivative of the internal energy U with respect to the number of particles Ni at the constant entropy S, the volume V and the number of particles Nj, where j is not equal to I. If we compare the equations in the second line, then we obtain another three expressions. In the first one, the temperature T is equal to the partial derivative of the enthalpy H with respect to the entropy S at the constant pressure P and the number of particles Ni. In the second one, the volume V is given by the partial derivative of the enthalpy H with respect to the pressure P at the constant entropy S and the number of particles Ni. In the third one, the chemical potential μI is equal to the partial derivative of the enthalpy H with respect to the number of particles Ni at the constant entropy S, the pressure P and the number of particles Nj, where j is not equal to I. We can derive further free expression by comparing the equations in the third line with each other. The first expression states that the entropy S is equal to minus the partial derivative of the free energy F with respect to the temperature T at the constant volume V and the number of particles Ni. The second one tells us that the pressure P is given by minus the partial derivative of the free energy F with respect to the volume V at the constant temperature T and the number of particles Ni. The third one states that the chemical potential μI is equal to the partial derivative of the free energy F with respect to the number of particles Ni at the constant temperature T, the volume V and the number of particles Nj, where j is not equal to I. The last group of expressions comes from the comparison of the two equations in the fourth line with each other. In the first expression, that the entropy S is equal to minus the partial derivative of the free enthalpy G with respect to the temperature T at the constant pressure P and the number of particles Ni. In the second one, the volume V is given by the partial derivative of the free enthalpy G with respect to the pressure P at the constant temperature T and the number of particles Ni. In the third one, the chemical potential μI is equal to the partial derivative of the free enthalpy G with respect to the number of particles Ni at the constant temperature T, the pressure P and the number of particles Nj, where j is not equal to I. We will use these four groups of equations to express each thermodynamic potential as an explicit function of the rest of the potentials and state variables. In order to provide such expressions, we will apply Euler's theorem for homogeneous functions, but first let us examine how the potentials scale with state variables. We saw that any thermodynamic potential phi I is a state function depending on the pressure P, the volume V, the temperature T of a system, and the number of particles Nj in the system in the absence of external forces. When we introduced the thermodynamic quantities describing the properties of an ideal gas, we classified them as extensive and intensive properties. We found that the volume V or the mass m, that is the number of the particles Nj of the gas, are extensive properties depending on the amount of matter present in the system. Since we interpret both the internal energy and the heat as quantities determined by the molecular motion in the kinetic theory of gases or any other substance, it can be shown that both internal energy and entropy depend on the amount of matter in the system. Then they are also extensive properties of a thermodynamic system. It is also true for the rest of the thermodynamic potentials defined by expressions in which the extensive quantities appear in sums or in products with intensive quantities. As a result, all the thermodynamic potentials phi I are extensive properties of a system. Among the state variables, only the pressure P and the temperature T are intensive properties independent from the amount of matter in the system. In order to specify the amount of matter in a thermodynamic system, we use the number of particles present there. If we scale the number of particles Nj with a factor lambda, then the volume V occupied by the particles also scales with the same factor. The thermodynamic potentials of a given system have the same scaling property, that is, the potentials are multiplied by lambda in a system with the number of particles lambda times Nj. Therefore, a potential phi I as a function of either on the volume V or on the number of particles Nj or on both of them can be evaluated at lambda times V and lambda times Nj, giving lambda times phi I evaluated at V and Nj. In mathematics, a function with such a property is called homogeneous function in the variables exhibiting this scaling property. We call a function f of n variables a homogeneous function of degree k in its first variables x1, x2, ellipsis, xm with m less than or equal to n, if the function f evaluated at lambda times x1, ellipsis, lambda times xm, xm plus 1, ellipsis, xn, is equal to lambda to k times the function f evaluated at x1, ellipsis, xm, xm plus 1, ellipsis, xn. Here lambda is an arbitrary real parameter. Now we compute the derivative of this equation with respect to the parameter lambda. By introducing the notation yi for lambda times xi, we can write the derivative of the left-hand side as the derivative of the function f evaluated at y1, ellipsis, ym, xm plus 1, ellipsis, xn with respect to lambda, and apply the chain rule for the function yi. Then we obtain the sum of the partial derivative of the function f with respect to yi at constant yj where j is not equal to I, times the partial derivative of yi with respect to lambda, from I equals to 1 to m. If we substitute the definition of yi into the derivatives, then we take the partial derivatives of the function f with respect to lambda times xi, and the derivative of yi with respect to lambda can be written as xi. Now we compute the derivative of the left-hand side of the definition of the homogeneous function f. The derivative of lambda to k times the function f with respect to lambda, is equal to k times lambda to k minus 1, times the function f. By inserting these two equations into the derivative of the definition of the homogeneous function f and setting the arbitrary parameter lambda to 1, we obtain Euler's theorem for homogeneous functions, which states the following. If a function f of n variables is a homogeneous function of degree k in its first m variables, then k times the function f is equal to the sum of the derivative of the function f with respect to xi, times xi from I equals to 1 to m. As the scaling property of the thermodynamic potentials shows, they are homogeneous functions of degree 1, and Euler's theorem for k equals to 1 can be applied for them. Now we apply Euler's theorem for the thermodynamic potentials to write them in a set of equations known as Euler integrals. In this table the first column contains 4 thermodynamic potentials as functions of their natural variables. Since the natural variables of the internal energy U are the entropy S, the volume V and the number of particles Ni, the internal energy of a thermodynamic system is a homogeneous function of degree 1 in all its natural variables. By applying Euler's theorem for the internal energy, we can write U as the partial derivative of U with respect to S at constant V and Ni, times S, plus the partial derivative of U with respect to V at constant S and Ni, times V, plus the sum of the partial derivative of U with respect to Ni at constant S, V and Nj, where J is not equal to I, times Ni and the index I runs from 1 to the number of the species n. We already determined the partial derivatives in this expression, and we saw that the first one is equal to the temperature T, the second one is equal to minus the pressure P, and the third one is equal to the chemical potential mu I. As a result, the internal energy U is equal to the temperature T times the entropy S, minus the pressure P times the volume V, plus the sum of the chemical potential μi times the number of particles Ni from I equals to 1 to n. The natural variables of the enthalpy H are the entropy S, the number of particles Ni, and the pressure P, but only the first two of them are extensive properties. Therefore, enthalpy is a homogeneous function of degree 1 in its first two variables, and it follows from Euler's theorem that the enthalpy H is equal to the partial derivative of H with respect to S at constant P and Ni, times S, plus the sum of the partial derivative of H with respect to Ni at constant S, P and Nj where J is not equal to I, times Ni from I equals to 1 to n. The partial derivatives in this expression were also determined, and we found that the first one is equal to the temperature T and the second one is equal to the chemical potential μI. As a result, the enthalpy H is given by the temperature T times the entropy S, plus the sum of the chemical potential μI times the number of particles Ni from I equals to 1 to n. The natural variables of the free energy F are the volume V, the number of particles Ni and the temperature T. Then the free energy is a homogeneous function of degree 1 in its first two variables, allowing us to apply Euler's theorem for it, and write the free energy F as the partial derivative of F with respect to V at constant T and Ni, times V, plus the sum of the partial derivative of F with respect to Ni at constant T, V and Nj where J is not equal to I, times Ni from I equals to 1 to n. We also know the partial derivatives in this expression. The first one is equal to minus the pressure P and the second one is equal to the chemical potential μI. Then the free energy F is given by minus the pressure P times the volume V, plus the sum of the chemical potential μI times the number of particles Ni from I equals to 1 to n. Since the natural variables of the free enthalpy G are the number of particles Ni, the temperature T and the pressure P, free enthalpy is a homogeneous function of degree 1 in its first variable. By applying Euler's theorem, the free energy G can be written as the sum of the partial derivative of G with respect to Ni at constant T, P and Nj where J is not equal to I, times Ni from I equals to 1 to n. Here the partial derivative is equal to the chemical potential μI, and the free enthalpy G is simply equal to the sum of the chemical potential μI times the number or particles Ni from I equals to 1 to n. The expression obtained for the internal energy U is also known as Euler equation in thermodynamics, and the four equations in the last column are called Euler integrals because they are derived by applying Euler's theorem. Although the last three equations are the consequences of the application of Euler's theorem, they immediately follow from the Euler equation. Since the enthalpy H is defined by the sum of the internal energy U and the product of the pressure P and the volume V, we can substitute into the definition the Euler equation, and write H as T times S minus P times V plus the sum of μI times Ni, plus P times V, then we obtain the equation in the third line of the table. Similarly, the free energy F is defined by the internal energy U minus the temperature T times the entropy S. By substituting the Euler equation into the definition, we have T times S plus P times V plus the sum of μI times Ni, minus T times S, which gives the equation in the fourth line of the table. Finally, the free enthalpy G defined by the enthalpy H minus the temperature T times the entropy S can also be seen as the consequence of the Euler equation, because the substitution of the expression obtained for the enthalpy into its definitions gives T times S minus the sum of μI times Ni, minus T times S, which can be reduced to the equation in the fifth line of the table. Now we can compare the fundamental equations in thermodynamics with the Euler integrals. Here we can see the five fundamental equations where the first two equations are equivalent to each other. We already saw that in these equations the differentials of the thermodynamic potentials are expressed as functions of the differentials of their natural variables. We also show the Euler integrals supplemented with the Euler equation solved for the entropy S, as seen in the second equation. These expressions present the thermodynamic potentials as functions of their natural variables, and we can write them in the following general form. If we denote the extensive properties among the natural variables such as the entropy S, the volume V and the number of particles Ni by calligraphic E, and denote the intensive properties appearing the Euler integrals such as the temperature T, the pressure P, and the chemical potential μI by calligraphic I, then any potential phi in the four independent Euler integrals can be written as the sum of Cij, times calligraphic Ij, times calligraphic Ej from j to 1 to the number of the terms in the right-hand sides of the Euler integrals. Here the multiplication factor Cij is defined by +1, -1, or 0 depending on the jth term in the ith Euler integral. Since the comparison of the first fundamental equation with the Euler equation shows the resemblance in their structures, we could assume the fundamental equations can be derived from the differentials of the Euler integrals. If we compute the differential of the potential phi I, then we can write d phi I as the sum of Cij times calligraphic Ej times the differential of calligraphic Ij, plus the sum of Cij times calligraphic Ij times the differential of calligraphic Ej. We can see that the right-hand side of this equation has terms with both the differentials of the intensive properties and the differentials of the extensive ones. This is not the case for the first fundamental equation containing only the differentials of the extensive properties. That is, the fundamental equation cannot be derived alone from the differential of the Euler equation. In fact, the fundamental equations and the Euler integrals are two sets of equations independent from each other. As a result, they can be combined to derive new expressions describing the relations between the potentials and the state variables of a thermodynamic system. Such an expression is the Gibbs-Duham equation, and we can derive it from the Euler equation and the first fundamental equation. The Euler equation states that the internal energy U of a thermodynamic system is given by the product of its temperature T and entropy S, minus the product of its pressure P and volume V, plus the sum of the chemical potential mu times the number of particles Ni from I equals to 1 to the number n of the species in the system. By computing the differential of the internal energy, we can write that du is equal to S times dt plus T times ds, minus V times dp minus P times dv, plus the sum of the quantity of Ni times d mu I plus mu I times dni. If we reorder the terms in the right-hand side, then we have T times ds minus P times dv plus the sum of mu I times dni, plus S times dt minus V times dp plus the sum of Ni times d mu I. The first fundamental equation states that the differential of the internal energy U is equal to T times ds, minus P times dv, plus the sum of mu I times dni. By substituting it into the differential of the Euler equation, we obtain the Gibbs-Duham equation stating that the sum of the number of particles Ni times the differential of the chemical potential mu I from I equals to 1 to the number n of the species in the system, is equal to minus the entropy S of the system, times the differential of its temperature T, plus the volume V of the system times the differential of its pressure P. We note that we can also obtain the Gibbs-Duham equation, if we compute the differential of the Euler integral stating that the free enthalpy G is equal to the sum of the chemical potential Mi times the number of particles Ni from I equal to 1 to n. Then dG is equal to the sum of the quantity of Ni times d mu I plus mu I times dni. At the same time, the last fundamental equation obtained for the free enthalpy G states that its differential is equal to minus S times dt, plus V times dp, plus the sum of mu I times dni. If we substitute it into the differential of the Euler integral, then we obtain the Gibbs-Duham equation. Since the differentials in the chemical potential, the temperature and the pressure appear in the Gibbs-Duham equation, the equation represents a constraint on the change in the chemical potential of a thermodynamic system in terms of the change in its temperature and pressure for a given composition of the system. In the case of isothermal and isobaric processes, the right-hand side of the equation vanishes, and we can write that the sum of the number of particles Ni times the differential of the chemical potential mu I from I equals to 1 to number n of the species in the system vanishes. For two-component systems we have only two terms in the sum, and we can express the infinitesimal change in the chemical potential mu1 as minus the ratio of the number of particles n1 to the number of particles n2, times the infinitesimal change in the chemical potential mu2. By comparing the fundamental equations in thermodynamics with the differentials of the thermodynamic potentials expressed in terms of their natural variables, we obtained four groups of equations describing the relations between state variables or potentials and the partial derivatives of the potentials. The first group was derived from the first fundamental equation describing the differential of the internal energy, where the temperature T, the pressure P, and the chemical potential mu I are expressed as the partial derivatives of the internal energy U. The second group was derived from the second fundamental equation describing the differential of the enthalpy, where the temperature T, the volume V, and the chemical potential mu I are expressed as the partial derivatives of the enthalpy H. The third group was derived from the third fundamental equation describing the differential of the free energy, where the entropy S, the pressure P, and the chemical potential mu I are expressed as the partial derivatives of the free energy F. The last group was derived from the last fundamental equation describing the differential of the free enthalpy, where the entropy S, the volume V, and the chemical potential mu I are expressed as the partial derivatives of the free enthalpy G. In the four groups of relations, there are two pairs of equations expressing the temperature and pressure as the derivatives of different potentials, and four equations expressing the chemical potential as the derivatives of the four potentials. This set of equations expressing intensive variables as functions of the thermodynamic potentials and state variables are called equations of state. In the Euler integrals, we express the thermodynamic potentials as functions of the entropy S, the temperature T, the pressure P, the volume V, the chemical potential μI, and the number of particles Ni. As a result, the equations of states expressing the intensive properties in terms of the extensive ones has the general form, where the temperature T, the pressure P and the chemical potential μ are expressed as functions of the entropy S, the volume V and the number of particles Ni. We note that there are also two pairs of equations in the four-group of relations where the volume V and the entropy S are expressed as the derivatives of the potentials. Since these are extensive properties, the partial derivatives in the right-hand sides provide an implicit dependence of the intensive properties on the extensive ones. Let us consider the four groups of equations describing the relations between state variables or potentials and the partial derivatives of the potentials again. We use these relations to express the thermodynamic potentials in terms of the entropy and the state variables in the Euler integrals. We will now use these four groups of equations to derive Maxwell's thermodynamic relations. In order to obtain these relations, we compute the partial derivatives of the first two equations in each group. For the first equation in the first group, we can write that the partial derivative of the temperature T with respect to the volume V at constant entropy S and the number of particles Ni is equal to the second-order partial derivative of the internal energy U with respect to the volume V and the entropy S. For the second equation, we have the partial derivative of the pressure P with respect to the entropy S at constant volume V and the number of particles Ni, which is equal to minus the second-order partial derivative of the internal energy U with respect to the entropy S and the volume V. For the first equation in the second group, we can write that the partial derivative of the temperature T with respect to the pressure P at constant entropy S and number of particles Ni is equal to the second-order partial derivative of the enthalpy H with respect to the pressure P and the entropy S. For the second equation, we have the partial derivative of the volume V with respect to the entropy S at constant pressure P and number of particles Ni, which is equal to the second-order partial derivative of the enthalpy H with respect to the entropy S and the pressure P. For the first equation in the third group, we can write that the partial derivative of the entropy S with respect to the volume V at constant temperature T and number of particles Ni is equal to minus the second-order partial derivative of the free energy F with respect to the volume V and the temperature T. For the second equation, we have the partial derivative of the pressure P with respect to the temperature T at constant volume V and number of particles Ni, which is equal to minus the second-order partial derivative of the free energy F with respect to the temperature T and the volume V. For the first equation in the last group, we can write that the partial derivative of the entropy S with respect to the pressure P at constant temperature T and number of particles Ni is equal to minus the second-order partial derivative of the free enthalpy G with respect to the pressure P and the temperature T. For the second equation, we have the partial derivative of the volume V with respect to the temperature T at constant pressure P and number of particles Ni, which is equal to the second-order partial derivative of the free enthalpy G with respect to the temperature T and the pressure P. If we apply Schwartz theorem on the symmetry of mixed partial derivatives in these four pairs, then we see that the right-hand sides of the equations are equal for each pair, and we obtain the following relations. The first pair of the equations gives the relation stating that the partial derivative of the temperature T with respect to the volume V at constant entropy S and number of particles Ni is equal to minus the partial derivative of the pressure P with respect to the entropy S at the constant volume V and number of particles Ni. For the second pair, we obtain the relation stating that the partial derivative of the temperature T with respect to the pressure P at constant entropy S and number of particles Ni is equal to the partial derivative of the volume V with respect to the entropy S at constant pressure P and number of particles Ni. The third pair of equations gives the relation stating that the partial derivative of the entropy S with respect to the volume V at constant temperature T and number of particles Ni is equal to the partial derivative of the pressure P with respect to the temperature T at constant volume V and number of particles Ni. For the last pair of equations, we can have the relation stating that the partial derivative of the entropy S with respect to the pressure P at constant temperature T and number of particles Ni is equal to minus the partial derivative of the volume V with respect to the temperature T at constant pressure P and number of particles Ni. These four equations are called Maxwell relations. They are derived from the first two equations of the four groups, but we can also compare the partial derivatives of the last equations in these groups with those of the first two equations to obtain additional relations. For the sake of simplicity, we present these additional relations in the case of a single-component thermodynamic system, where n denotes the number of particles for a given gas or other substance. Here we repeat the four basic Maxwell relations for the single-component system, and supplement them with the relations obtained by comparing the partial derivatives of the first two equations in the four groups of relations with the partial derivatives of the last ones depending on the chemical potential. If a system remains in chemical equilibrium during a thermodynamic process, then the chemical potential of the system is constant, and only the first four Maxwell relations are relevant in the study of the process. As opposed to the fundamental equations or the Euler integrals, these expressions contain only the derivatives of thermodynamic variables and describe the relations between them. However, these relations are useful to express quantities which are difficult to measure in terms of those which can be measured in a laboratory. A frequently cited example for such a situation is the relation between the specific heat capacities of a given substance. When we study the relation between the internal energy and the heat capacity of a thermodynamic system, we derived the equation stating that the difference between its specific heat capacity Cp at constant pressure and Cv at constant volume is equal to 1 over the mass of the given substance in the system, times the sum of the partial derivative of the internal energy U of the system with respect to its volume V at constant temperature T, and the pressure P in the system, times the partial derivative of the volume V with respect to the temperature T at constant pressure P. In a general situation, it is not convenient to determine the derivative of the internal energy of the system. Nevertheless, the internal energy U of a given amount of gas can still be expressed as a function of its entropy S and volume V, where the number of the particles n is a fixed parameter now. If the ideal gas approximation holds for the gas, then we can use the ideal gas law stating that the product of the pressure P and the volume V is equal to the mass m of the gas, times its specific gas constant Rs, times the temperature T, which allows us to derive an explicit formula for the internal energy of the ideal gas. In the general case, we can apply the chain rule for the derivative of the internal energy given as a function of entropy and volume V, and write the partial derivative of U with respect to V at constant T, as the partial derivative of U with respect to V at constant S, times the partial derivative of V with respect to itself at constant T, plus the partial derivative of U with respect to S at constant T, times the partial derivative of S with respect to V at constant T. For the first factors of the two products in the sum, we can apply the equations of states for pressure and temperature presented before the derivation of the Maxwell relation. We can also substitute the third Maxwell relation into the derivative of the entropy in the second term. As a result, the first term is equal to minus the pressure P, since the derivative of V with respect to itself is 1, plus the temperature T times the partial derivative of the pressure P with respect to the temperature T at constant volume V. In the general case, it is not so difficult to measure the change in the pressure as a function of temperature in a constant volume, and the left-hand side of the derivative of the internal energy can be determined. In the case of an ideal gas, we can substitute the ideal gas law into the derivative, which gives minus the pressure P, plus the temperature T times the ratio the mass m times the specific gas constant Rs divided by the volume V. But the second term is just equal to the pressure P as the ideal gas law shows, and the right-hand side vanishes. It is also obvious from the fact that the internal energy of an ideal gas does not depend on its volume. Then the general relation of the specific heat capacity reduces to Meyer's relation, as the substitution of the ideal gas law into the partial derivative of the volume V with respect to the temperature T at constant pressure P gives the ratio of the mass m times the specific gas constant Rs to the pressure P. By inserting this result into the original relation, the difference between the specific heat capacities can be written as 1 over m times P, times the ratio of m times Rs to P, which is equal to the specific gas constant Rs providing in Meyer's relation. We already presented several thermodynamic relations such as the fundamental equations or the Maxwell relations, and there is a mnemonic diagram called thermodynamic square to derive these relations for one-component systems. First, we will show how to reproduce the fundamental equations by applying the thermodynamic square. The diagram consists of the letters of state variables and thermodynamic potentials arranged around a square. The thermodynamic potentials, that is the internal energy U, the enthalpy H, the free energy F and the free enthalpy G are written along its sides. At the corners we see the entropy S and the state variables, that is the volume V, the pressure P and the temperature T. The minus signs in the front of the entropy S and the pressure P are in use when these quantities appear in the fundamental equations as mere state variables. If they are the natural variables of the potential for which the differential is written in the left-hand side of the equation, then we will drop the negative sign. For the first fundamental equation, we choose the letter U at the top of the square for the differential of the internal energy in the left-hand side of the equation. One of the neighbor of the internal energy U in the diagram is the entropy S at the top left corner of the square, representing one of the natural variables of the internal energy. Then the differential of the entropy S appears in the right-hand side with a plus sign because entropy is a natural variable. The other neighbor of the internal energy U is the volume V, representing its second natural variable, and it appears as the second differential in the right-hand side of the equation. The quantity at the diagonally opposite corner of the entropy S is the temperature T, which becomes the positive multiplication factor of the differential of the entropy in the right-hand side. Since we find the pressure P at the diagonally opposite corner of the volume V, it will be the multiplication factor of the differential of the volume with a negative sign, as the pressure is not a natural variable of the internal energy. As a result, we obtain the first fundamental equation. In order to reproduce the second fundamental equation, we choose the enthalpy H at the right-hand side of the square with its differential of the left-hand side of the equation. The two neighboring quantities of the enthalpy in the diagram are the entropy S and the pressure P, representing the natural variables of enthalpy, and we can write their differentials in the right-hand side of the equation. The diagonally opposite corners of the natural variables S and P are the temperature T and the volume V respectively, and they appear as the multiplication factors of the differentials in the right-hand side. This gives the second fundamental equation. For the third fundamental equation, we select the free energy F at the right-hand side of the square for the differential in the left-hand side of the fundamental equation. The neighboring quantities of the free energy in the diagram are the volume V and the temperature T, representing its natural variables, and their differentials appear in the right-hand side of the equation. The diagonally opposite corners of the natural variables T and V are minus the entropy S and minus the pressure P, and they can be written as the multiplication factors of the differentials in the right-hand side. Then we obtain the third fundamental equation. If we choose the free enthalpy G at the bottom of the square, its differential can be written in the left-hand side of the last fundamental equation. The neighboring quantities of the free enthalpy in the diagram are the pressure P and the temperature T, representing its natural variables, and we can write their differentials in the right-hand side of the equation. The diagonally opposite corners of the natural variables P and T are the volume V and minus the entropy S, and they appear as the multiplication factors of the differentials in the right-hand side. This gives the last fundamental equation. The thermodynamic square can also be used to derive the Maxwell relations. Here we only need the variables at the corners of the square, and the minus sign is applied if the entropy or the pressure is the dependent variable in the partial derivatives appearing in the relations. For the first Maxwell relation, we choose the temperature T at the bottom right corner of the square to express the partial derivative of the temperature T in terms of another thermodynamic variable at any of the neighboring corner. Here we select minus the pressure P at the bottom left corner, appearing in the derivative in the right-hand side of the relation. The minus sign is used for the pressure as a dependent variable of the derivative. Since we need to rotate our position at the temperature clockwise by 90 degrees to get to the corner of the pressure P, we rotate our position anticlockwise and select the volume V at the adjacent corner of the temperature T, applied as the independent variable in the derivative of the temperature. If we rotate our position by 90 degrees further, then we reach the corner of the entropy S, and obtain the constant parameter of the derivative of the temperature with respect to the pressure. We follow the same procedure for the derivative of the pressure P in the right-hand side of the Maxwell relation. Since we need to rotate our position at minus the pressure P anticlockwise to get to the corner of the volume V, we rotate our position clockwise and select the entropy S at the adjacent corner of the pressure P, applied as the independent variable in the derivative of the pressure. If we rotate our position by 90 degrees further, then we reach the corner of the volume V, and obtain the constant parameter of the derivative of the pressure with respect to the entropy. As a result, we have reproduced the first Maxwell relation, and the same algorithm can be used for the rest of them. For the second relation, we start with the temperature T again, but we choose the volume V at the adjacent corner and write their partial derivatives in the two sides of the relation. Now we rotate our position at the corner of the temperature T clockwise and reach the pressure P at the adjacent corner, applied as the independent variable in the derivative of the temperature. A further rotation gives the position of the entropy S, which serves as the constant parameter of the derivative of the temperature with respect to the pressure. For the partial derivative of the volume V in the right-hand side of the relation, we rotate our position at the volume V counterclockwise and select the entropy S as the independent variable in the derivative of the volume. By rotating our position further, we reach the position of the pressure P, and apply it as the constant parameter of the derivative of the volume with respect to the entropy. Then we have obtained the second Maxwell relation. For the third Maxwell relation, we choose minus the entropy S and minus the pressure P, and write their partial derivatives in the two sides of the relation. Since both of the dependent variables are negative, we drop the negative sign. The clockwise rotation of our position at minus the entropy S gives the position of the volume V used as the independent variable in the derivative of the entropy. From a further rotation, we obtain the position of the temperature T, serving as the constant parameter of the derivative of the entropy with respect to the volume. Similarly, we rotate our position at minus the pressure P counterclockwise and reach the position of the temperature T, which is the independent variable of the derivative of the pressure now. Then we rotate our position further and arrive at the corner of the volume V, and apply it as the constant parameter of the derivative of the pressure with respect to the temperature. This gives the third Maxwell relation. For the last Maxwell relation we start with minus the entropy S again, but we choose the volume V at the adjacent corner and write their partial derivatives in the two sides of the relation. Since minus the entropy has the sign opposite to the one of the volume, we write a negative sign in the right-hand side. Now we rotate our position at the corner of the entropy S counterclockwise and reach the pressure P at the adjacent corner, applied as the independent variable in the derivative of the entropy. A further rotation gives the position of the temperature T, which serves as the constant parameter of the derivative of the entropy with respect to the pressure. For the partial derivative of the volume V in the right-hand side of the relation, we rotate our position at the volume V clockwise and select the temperature T as the independent variable in the derivative of the volume. By rotating our position further, we arrive at the position of the pressure P, and use it as the constant parameter of the derivative of the volume with respect to the temperature. Then we have obtained the last Maxwell relation. The thermodynamic square can also be reproduced by using a mnemonic sentence, where the first letters of the words are the variables arranged around the square. For example, we have such a sentence stating that the friendly vagabond usually shares his precious gifts. In this sentence the list of variables starts with the temperature T at the bottom right corner of the square, and the variables are arranged counterclockwise around the square. Another mnemonic sentence helping to remember the order of the variables is the following: good physicists have studied under very fine teacher. Here the list of variables starts with the free enthalpy G at the bottom of the diagram, and the variables are arranged clockwise along the sides and corners of the square. In fact, it does not matter at which corner or side of the square we start to write the letters, as long as their order remains the same, preserving the relations between the quantities arranged around the square. In the end of this presentation on the second law of thermodynamics and entropy, we will give a summary of the topics discussed here. We started with the discussion on the direction of thermodynamic processes in nature and presented the second law of thermodynamics in two forms. In the form introduced by Kelvin and Planck, the second law states a perpetuum mobile of the second kind cannot exist, or it is impossible to construct an engine that extracts heat from a thermal reservoir and converts it to work without producing any change. The second law formulated by Clausius tells us that heat can never pass from a colder to a warmer body without some other change, connected therewith, occurring at the same time. We use the second law to divide processes in nature into reversible and irreversible ones, and to prove Carnot's theorem stating that the thermal efficiency of a reversible Carnot cycle is independent of the material properties of the thermodynamic system performing the cycle. This statement also helped us to redefine the thermodynamic temperature based on the measurement of the thermal efficiency of a heat engine with a heat source of a reference temperature. Based on Carnot's theorem, we proved Clausius inequality stating that the sum or the cyclic integral of the reduced heat produced in each step of a thermodynamic cycle is less than zero if the process is irreversible, or equal to zero if the process is reversible. We use this inequality to study the thermal efficiency of heat engines, and show that the heat cannot be completely converted into work by a heat engine in a thermodynamic cycle. We also applied Clausius inequality to define the entropy of a system at a given state by the integral of the reduced heat of the system along a reversible path of a process from a reference state to the given state. The differential form of this definition helped us to reformulate the second law of thermodynamics stating that the infinitesimal change in the entropy of a system given by the infinitesimal amount of the reduced heat absorbed by the system in a reversible process is an exact differential. As a result, we could express the second law as the principle of entropy production stating that the entropy of an isolated system always increases during an irreversible process or remains constant during a reversible one. We also determine the entropy of an ideal gas and discuss the production of entropy for various processes in nature such that the free expansion of air, heating, mixing and Carnot cycle. Then we define the Helmholtz free energy of a thermodynamic system by the difference between its internal energy and the bound energy given by the product of the temperature and the entropy of the system. We demonstrated that the decrease in free energy measures the maximum work that can be done by a system during an isothermal process in a reversible limit. We also saw that in an isothermal and isochoric process the free energy of a system decreases until the system reaches equilibrium and the free energy attains a minimum. Then we define the free enthalpy or the Gibbs potential of a thermodynamic system as the difference between its enthalpy and the product of the temperature and the entropy of the system. We proved that the decrease in free enthalpy measures the maximum work apart from pressure volume work that can be done by a system during an isothermal and isobaric process in a reversible limit. We also saw that in such a process the free enthalpy of a system decreases until the system reaches equilibrium and the free energy attains a minimum. By adding the definitions of free energy and free enthalpy to the list of internal energy, enthalpy, and entropy, we introduced the concept of thermodynamic potentials. In general, we demonstrated that the extremum principle holds for all the thermodynamic potentials determining the direction of thermodynamic processes, and establishes the criteria for thermodynamic equilibrium. We derived the fundamental equations of thermodynamics expressing the infinitesimal change in the thermodynamic potentials in terms of state variables, potentials, and the differentials of the natural variables of the corresponding potential. We used the fundamental equation for entropy to determine the conditions for thermal, mechanical, and chemical equilibrium in an isolated thermodynamic system, and we saw that these conditions prescribe uniform temperature, pressure, and chemical potential throughout the system. Then we proved Euler's theorem for homogeneous functions, and applied it to determine the Euler equation in thermodynamics and the further Euler integrals from the fundamental equations. We could use these Euler integrals expressing thermodynamic potentials in terms of the state variables to derive the Gibbs-Duham equation, which is a constraint on the change in the chemical potential of a system in terms of the change in its temperature and pressure for a given composition. Finally, we introduced Maxwell's thermodynamic relations between the partial derivatives of the state variables of a system. In an example of the relation between the specific heat capacities at constant pressure and volume, we illustrated how Maxwell relations help us to express thermodynamic quantities in terms of those which are not difficult to measure. We also presented a method using a mnemonic diagram called thermodynamic square to reproduce both the fundamental equations and Maxwell relations.